you doing? Good? So, live stream, start up. It's embarrassing. Okay. Hey. All right. So we'll just spin this up. All you need today is Google Colab. That's all you're going to need.
Is there any slides already?
There is slides, yes. I can give you the links to them, yeah. Okay, cool. So this is streaming from the hackerhustle.com. Cool. So this is streaming from and I'm just trying to figure out that chat. If that doesn't work, we'll set up a WhatsApp chat like we did last week. Okay, cool. So that's working. So if you're on the live stream, you should be able to message here. Also, if anybody who is here in person has any questions throughout the session, feel free to either raise your hand and I can answer, or put a response here. and Haroon is going to be here in a second. And he'll be able to answer those whilst I'm going through this stuff. But that's basically the deal, and that's going to be the deal for anything that we do from now on, which you'll be able to keep up to date with either through this website, myself, social media, or email. But yeah, basically today, if you want to rewatch this stuff later, we'll put it online, and if you want to ask questions without shouting out in front of everybody now, you can put it here, and we'll get back to you there. But what are we going to be doing today? So basically, we're going to firstly walk through these slides on the foundations of like strong machine learning foundations, and then we're going to basically just discuss like throughout that like what is AI and how do we make it, and then either we will go into a basic implementation to show you some of that stuff in code, or depending how we're feeling, we'll go to the theory of like neural networks and deep learning, and then we'll do all the implementation at the end. So, okay, I guess that's long enough for everybody to get here. But yeah, basically, please ask questions all throughout. I really want to make sure everybody understands this, and if there's anything that's not clear, just let me know. But okay, let's get started. 5 minutes in. So these slides are about foundations of machine learning. So what we're going to go through in these slides is what we're trying to do when we talk about machine learning, what makes a machine learning algorithm, and part of that is parameter estimation, which we'll talk about. Then we'll go over bias and variance, what those things mean, and how they can affect the performance of our models, and what we can do to combat them. Then we'll talk about maximum likelihood, which is a way that we most commonly train machine learning models. And then we won't go through the traditional stuff today, I don't think. So, most generally, with machine learning, what we want to do is map some input to some output. And that can be anything, really. So, some examples here, like we can map text to its sentiment. Is this a positive or a negative sentence? If we're doing something like movie reviews. Images to boxes that bound specific objects within them, so that's object detection, computer vision. Medical images, classifying prediction of a condition. These are all just input to output, and that's really like what you need to think of machine learning as. Another example might be previously purchased items to future items that you might purchase. That means we're trying to find some, I should probably say something like trying to find some function to map between those things. And so we will, I don't know why this cut off. We'll spend the rest of today like exploring how to come up with these mappings and model those input-output relationships. But that's really all we're doing. We're trying to find functions which take in an input and output the output that we want. And that is prediction. That's what we're trying to do. Just trying to predict the correct output using some model. And so those functions, they are literally purely just mathematical functions, and they can be of any form, really. So in the left, like you see, like they can be nonlinear. So this is a function which is influenced by the first order of the input, second order, and the third order, and it has some offset term here. But these are all these green things here. They're just the parameters of the functions. So yeah, they can be nonlinear, they can be high dimensional, so in that one, it's a plane, it's your prediction, and again, it's just like the orientation and the offset of that plane they're controlled by parameters, and that's what we were trying to learn in that case. They can also be probability distributions, so again, here is just some function. If our output is a probability, i.e. like a confidence, is this tumor benign or malignant? That will be the output, and this would be the model, which in this case is like a bimodal Gaussian distribution, again just controlled by parameters. So it's got weightings for each of those distributions, it's got different centers and different spreads for each of them. And they can also have many inputs and many outputs. Really, like the problem isn't, we're not constrained to any or at least what we want to do is be able to model functions which there is no limit on how many inputs they take and how many outputs they output as well, right? We just want to do this totally generally. So we're just going to learn this like super general class of functions. That's what we want to be able to do, to learn those inputs to outputs. Okay? Any questions about that? Cool. So how are we going to do this? Basically, making a machine learning implementation consists of 4 things. Firstly, the model. So that's the function that we're going to pass our data through and have produce our output. We're going to need the data, and that's going to determine what we're trying to learn. So we basically, in the case of supervised learning, where you have a mapping between input and output, i.e. you have a label, then that's what the data is going to be. And that's what you're going to show your model. I want you to try and replicate this behavior. So yeah, the data is what the function maps between the inputs and outputs if you have a label for it. We're going to use a criterion, or more commonly a loss function. And the point of that is just going to be to evaluate how badly our model is performing at the moment. And then over time, we're going to try and basically take that criterion, that loss function, and minimize it. So to minimize how badly our model is performing, in the hope that we'll get a model doing something that we want. And to do that, we're going to use an optimizer. So an optimizer defines how we'll make adjustments to the model, like how we'll change the parameters to improve its performance based on the loss function. Okay. So who knows what linear regression is? Okay. So linear regression is basically where you have your inputs and your outputs, and you're trying to find a model that maps between those two things. And in linear regression, you have a linear model. What that means is that the output is a weighted sum of the inputs. So say we have 3 inputs. Say we're trying to predict house prices. So we've got one single output, right? Scalar output, the price of the house, and we've got 3 inputs, like the age of the house, the number of rooms of the house, and the size of the garden of the house, right? We're going to say, with a linear model, in the case of linear regression, that the output is a weighted combination of those 3 inputs. So we'll have like some value times the number of rooms, some value times the number of times the age, and some value times the, whatever I said, the size of the garden. And so that like weighted sum of those inputs will be the output. So the model looks like that. So just written in matrix form. So this would be like a vector of 3 different weights in the case I was talking about, and this would be a vector of 3 different inputs for that particular example. So basically, we're just multiplying each element in here by the corresponding element in the input. So, and then we sum those up. That's what that multiplication means, and then we add some offset. So in this case, this would be like the price of the house, which I predict. That's what that hat means on that y. It's a prediction of the actual y, which is the label, is equal to a weighted combination of the inputs plus some offset. Is that clear? Should I go over that again? Is anybody not clear about that? Okay, cool. Right, so yeah, and like that could be anything, right? But that's the case. That's what a linear model looks like. So yeah, you got predicted label, you've got the parameters of the model, you've got the offset, and the linear model. So this part, just in case anybody's not clear, is if you've got a house which it's brand new, so age is 0, or say you've got a plot of land, it's got 0 rooms and it's got no garden. Well, it's not worth nothing, right? So it's got some offset here. So even if all of these values were 0 in this vector, then what you would have is some offset, like, okay, the land is worth something. So it has, when all those values are 0, it doesn't pass through the origin of this output. So Haroon is here. So if you have any questions, just put them on the Discord chat on Hackcastle TV. I emailed that link to everybody, so that's that you should have that in your email as long as you signed up for the event. And yeah, that's how we're doing it. So let's continue with the linear regression example, talking about those 4 things that we need. First one was the model. Second one is the data. And so, like, what that looks like here is a set. That's what these curly brackets are. A set of different examples. So this is like just denoting this is the whole data set, this big X. and then each example is one of these elements in here. So each of these example is like a different vector representing the different features for different houses. In this case, we've got m houses, all right? So we've got m examples with n features, and each of those examples looks like that, right? Is that clear? Cool. So yeah, again, like this data here is just going to be weights. In this case, it would be n weights, and they would each correspond to how much one of these affects the output. I.e. what you multiply it with. So yeah, just like another note on linear regression to make that really concrete for people is the three features I mentioned. So like age of the house, what's good ones? Yeah, age of the house, number of the rooms of house, and let's say age of the person who lived there before, right? So the age of the house, what kind of a weight is that going to have? Well, as a house gets older, it's probably worth less, right? So in that case, we could expect a negative weight. So that as the age of the house increases, we're actually taking away from our predicted price. The number of rooms of the house, well, if it's more rooms, it's bigger, and generally that means that it's going to be worth more, right? So in that case, we'd have a positive weight. And in the final feature, which I said was the age of the person living there before, well, how does that affect the price of a house, right? Like, not very much, okay? So in that case, you'd expect that weight, if we learnt it, would be 0, or roughly around there. Maybe it does influence it, I don't know, but just you can think of that intuitively. The next part of the model is criterion, so the loss function. In this case, this is an example of regression. What that means is we're predicting a continuous output. So if we're trying to look at our label, that y hat, and we have a true label, y, and we want to compare them, and have some measure of like how bad is our model, i.e. how different is the prediction to the label, then we can use, in this case, the mean squared error. So just walk through that. So what it is basically the difference between the prediction here, for this example I, and the label for this example I. So we have, each of these will be a different prediction for a house price and a label for a house price. To take the difference of them by subtracting the label from the prediction, then square them to make it positive. So whether I'm predicting above or below the correct answer, that will always contribute positively to this overall loss. And then I'll just average this over some mini batch, so like a group of houses, not just on one. So I'll take, like, I look at the predictions I have and the labels I have for 16 different houses, average that squared error over them. So that's a mean squared error loss function. And that's basically like the only one you really need to know about for regression. So this can be used for mapping, for trying to regress continuous output. So if you have any continuous label, house price, or whatever, like then you can just then you can try and learn it by evaluating a model on this loss function. Any questions about this so far? Cool. And then we have an optimizer, in this case, a simple optimizer. It's called stochastic gradient descent, SGD. And so what this does is what you'll do is you'll take a mini batch of size m, and then you'll evaluate the loss like that, and then you'll update the model by moving the weights by a very small amount in a direction which reduces that loss. So the way we're doing that is that this is differentiable. Do you know what I mean when I say that? Like, we can find the gradient of this, so we know how this changes as we change like the values which make it up. So we can find how does this change as our weights of our model change. So as our weights of our model change, this prediction will change, and then we can see, well, either our prediction will get closer to the label or further away. So we want to take our, sorry it's really small, but we're going to get our weights and we're going to set them equal to what they were minus some step size parameter, little step in the direction that reduces the loss. So that negative gradient is what is the direction which moving those weights in will reduce the loss. And that alpha there is called a learning rate. And that learning rate is basically just, well, if the gradient's really high, like, okay, it means I need to move in the opposite direction to that, but I don't want to move by a massive step. Maybe I'll just totally overshoot where I want to go to. So we just control the step size with that parameter alpha there. Okay, is that clear? Cool. Yeah, so that's like a full end-to-end example of how you would, how you build a model there, what the data would look like. Obviously, it's slightly different in code. How you would evaluate how bad the model's doing, and then how you would improve that model. Okay. So yeah, that's just like an expectance there. So yeah, this is an average, right? As I'm sure you can see, but it's an average over this thing here. So this is p hat data. What that means is that the data which you're looking at, the actual data which you have in your data set, has some distribution, right? It's like it's spread out in some way, and what you're hoping is that the way that your data is spread out looks like the way that data is spread out in the real world. So if you have a collection of images, you hope that the way these images look is kind of representative of how all images look, or how all images of dogs look, or something like that, right? But you don't have all images of dogs. You only have an empirical distribution, which is what this hat on that means there. Is it too small for people? So I'll make that bigger next time. I will do that, okay. Yeah, so just a note, like we're taking an expectance over this empirical distribution of the data, and this is sampled from, this is a mini batch sample from the whole data set. So that leads us to talk about data distributions. So, distributions are just functions that take some input and return how likely observing that input is, right? So you have p of x, like this is how likely you are to see x. In this case, I mean, here's an example of distribution, a uniform distribution, where x is always whatever x is, as long as it's between b and a, it's always the same probability over that whole range. So a normal distribution looks like that, right? It's centered around a mean. It's got some spread controlled by the standard deviation, and if you integrate it, it sums to 1, and it's always positive. That's basically the rules. So yeah, I mean, obviously for all distributions, they all need to sum to 1 over the whole space, and they need to be positive everywhere. Or a direct distribution, that's where it's p of x equals 0, except where x equals this special value, and it's like, okay, it's always going to come out there. So that's how you can think about deterministic things, even as distributions. So my point is, we have a load of distributions which we need to look at. One of them is called the data generating distribution. This is p data. This is the true distribution. What does the data actually look like? Like, how is it spread out? So think about if this x is house prices, well, maybe these are the kind of things you observe. So it's like, okay, a lot of houses are priced like this, a lot of them like this. There's a kind of dip in the middle. None of them are really priced any lower than this, and it's really rare that they're higher than this. Okay, so that's like a distribution of how some data could be laid out, and that's a one-dimensional example, right? So just bear that in mind. Like, this could have many axes, and they could have distributions all the way along in every direction, depending on how that particular feature might be distributed. So then we have the empirical distribution. So if you look at those orange dots there, that's p hat data. So these might be, well, if this is how all houses are actually distributed, well, these orange ones, like, these are the examples I have. This is how I can see they're distributed from my data. Like, this would be the statistical observation from the data set you actually have. So that's only a subset of the total data set, and that's the important thing to remember. Basically, the point of machine learning these days is powered by data, and a good data set means your empirical distribution looks like the real distribution. So it's like you can actually try and hope to model the thing you want to model, which is this blue line. Okay. In this case, like, I've drawn kind of a weak example here, so we'll see, like, if we learn to fit this empirical distribution with our model, so like say our model was predicting a distribution, then we might learn something like this, right? It's like it gets pretty close to all of those points. So wherever input you enter, it kind of gives you like, okay, yeah, I did kind of see the same thing as I saw in the data set. So according to the data set, like, that's a good model. However, that model distribution looks pretty different to the data generating distribution, right? And that's just because your data set hasn't covered what the model should do in certain places, you know, particularly like beyond here and beyond here in the other direction. Okay. And so, regardless of how good our model is, of how good our optimizer is, of how good the loss function is, if we don't have good enough data, then that's what our model might end up looking like, right? So it's like, it'll work for the cases where you've shown it to work. It worked for the data you've shown it, but not for other cases. So like if you're doing computer vision, you only take photos at night, then you try and show it once in the day, when you deploy it, it's probably not going to work. And that's just the point of like, okay, well maybe all of these were images which were taken in the dark, so we can't model them, something like that. And then another thing to note is like, we don't train on the whole data set. We'll only train on most of the data set because we want to save some of the data set for testing. If we train on it, well, it's like, you know, knowing the answers to the test we're taking. So we'll only train on these on these ones I've circled in purple. So it might be the case that like, yeah, so when we're training the model, we're actually not looking at these two orange examples here. We don't know what they are. But if the training distribution again like is representative of the empirical distribution of our data distribution, then we might be able to try and, you know, get a good output for these ones, even though we haven't seen them during training. Okay, is that clear? Cool. All right. So now, right, we know that what we're trying to do. We know all about the data now. You've heard me say that enough times. We know what we're trying to do is we're trying to find a function. A function to take in the input and output the output. And what that means is, you know, we can determine like what the function is. Okay, so what components does it have? Is it like, you know, add up different order polynomials and then add like a sine term of the input, or add like, you know, some Gaussian thing to it? We can build whatever models we want, right? We can just say like output equals all those different things, any different function of the input, or any constants, etc. But once we've set what the model looks like, what can really determine what it does is the parameters of the distribution of the model. So that is like the weightings of different parts of the model, and you know, so like if we have you know, if we have like an x squared term in there, like, well, it's something times x squared, i.e. how does that x squared really contribute to the output? And we're just trying to learn those parameters. So, so I think I'll show that in a sec. So almost all models that we're building are parametric, and that just means like they have parameters that change what they do. And yeah, like that. So here's our linear model, right? These are the two parameters. So it's those two kind of things. We just got, you know, we're going to just use the first order of x, and we're going to have a constant. Those two things are parameters of the model, and that's what we're trying to estimate, right? If we can do a good job of estimating them, then we can just come up with a good model and have the function we want to model. Okay. So yeah, given the architecture, that's what I'm saying. Given the architecture of the model, like whatever terms you decide to put in here, it could be like plus sine x, plus Gaussian distribution of x, etc. The goal is to estimate the parameters of those things, so like the coefficients or different parameters within them. So yeah, that's the point. And the question is like, well, what parameters are these? What qualities do they have? And hence, as you'll see, like, why do we use mean squared error? Why not like mean quadratic error or something like that? Mean quartic error, I mean, something like that. Okay, so firstly, just talk about bias. So what is bias in a model? Bias is the expected difference between the parameters you predict and the actual like true good parameters. If this model can model the data, then it'll need some parameters to do so, and this is like what they should be. So we don't really know this, but if we have a biased model, then on average, every time we learn new parameters for this model, they'll be different to what the actual parameters might be, the ideal parameters. So in this case, like, say we have this this green distribution which we're trying to model, but we're only using a linear model, right? Well then, well then the parameters of that define what this curve looks like are not going to be equal to the ones that we predict with this. So in this case of the red line, you can think like, well, our model looks like prediction equals something times x plus 0 times x squared, right? And so every time we build this linear model, we're going to have 0 times x squared because we haven't included an x squared term, which means that if this distribution is meant to have some x squared term in, like maybe we've just made it ourselves and we put an x squared term in there, then the x squared term should be non-zero. But really, we're just, if we're using this linear model, we're having a 0, and so there's a difference between those two things. That's that difference there, and then that's, averagely every time we do that, it's going to be different, so we have a biased model. Intuitively, the point is that the model is estimating something that we don't actually want. It's estimating something different. And so what that causes, like, when we train, the loss evaluated by our loss function, it does go down, like that, but it'll only go down to a certain point. It'll plateau, because like what I've drawn there is kind of like something like that. It's probably like the best fit you can get for that data with this linear model, right? So it might start off really badly, like it might start off coming down like that might be the line we're predicting, and over time, as we improve the gradient and the slope, the gradient and the intercept, which are the two parameters of a linear model, then it'll become something more like this. It will get better, that is, the loss will go down as we train over more examples, but it will only go down to a certain point because this is as good as it can get. Really, we want the loss to be as low as possible. And I mean, when you're training, like you will see the loss plateau, but you want its plateau low, or at least you want to test that it's doing a good job of modeling what you want before you say, okay, it's low enough. So what it causes is the model fails to capture the true input-output relationship. So if we learn this, we're just saying, well, when we have this input here, I predict it to be here. Really, it's there, so that's different. And that's called underfitting. So, so the model hasn't captured the input-output relationship that we want. So what can we do about it? We can make a more complex model. So like we could include more terms in a model, we just make a more complex model. You can do that in a bunch of different ways. That means increase the capacity. That's what that word means. It just means increase the complexity of the model. So that means you can model more complex functions. Maybe that means like including a quadratic term. Then you might be able to model this. Or in some cases, we can change the objective function, which is change the loss function, which we're trying to learn, but don't really worry about that. Okay. Any questions about bias? Okay. Okay, so variance is the other side of the coin. So bias basically means like the model is going to underfit and not capture the relationship we want, or not capture the relationship we want to in the data we have. Variance is the other side. So this is where it's going to overfit, and it's going to capture exactly the relationship of the data we show it. But really, we have to be careful because that data doesn't represent all data that could exist. So we don't want to, just fit to the data we have and not be able to generalize to further examples. So that's what variance looks like mathematically. There's not really that much point in looking at these equations, but because you don't know what this term is. But anyway, like that's what it is. So the variance is the expected difference, the expected square difference between like the parameters which you'll learn and the mean of the predicted parameters. So basically, if you're always predicting the same parameters, then the mean of those predicted parameters will be the same as this one, and this variance will be 0. So it's basically like how wildly can the parameters differ every time you train a model. And you'll see, just keep that in mind. There's a diagram there at the end. But this is like what a low bias, high variance model might look like. So here's the same distribution again. And what we've got now is that, well, if we look at the training error, like it's great, cool. It got like 0 loss. It passed through every single example perfectly. But then what you have is like, okay, again, this isn't a good model. Why? Because you can see if I try and predict the output this x value, well, it's wrong. And yeah, okay, so yeah, and so like you can see like there's many different ways. If I can draw a line as wavy as I want, then there's many different ways I could draw it through all of these points and still get the same, you know, zero error, right? So we could, you know, we could just take these peaks higher and it would still get the same error, but it would be a totally different model, it'd be different parameters. Which means that, you know, during training we could come up with a different parameterization that was just as good. It's just by chance that we've come up with this one. So the best parameterization varies with data from the same distribution. So that is like, if we train on different examples, we might get you know, different models, because if we only train on these first ones, yeah, I think there's an example of that down there, so we'll just go to that. Basically, what it causes is great training loss. So, you know, we can go exactly through all the points we want to, but an awful validation loss. So validation is when you're going to test your model on examples which aren't in the training set, different subset which you've excluded. Yeah, this is overfitting, as you can see. You know, it's like it should be intuitive, like that's overfit to that data. Yeah, the parameter estimates are really variable for these distributions. So that's kind of like what the loss curve will look like, right? So as you train, the training loss will get really, really low. Like, cool, we're passing through all of them, but the validation loss will just plateau. Like, so say we have validation examples which are like between these peaks. Well, it's not going to be able to capture them. It might even get higher. So this is the diagram I'm talking about. So if we train on different subsets of the data set, so like when we do our splitting the data set into training and testing, we'll get different empirical distributions, right? Different training distributions. And if we learn to fit those, then what we'll have is like, well, you can learn totally different models, right? And all of these, so say this purple and this yellow one, they're like two linear models. Well, the difference between their slope and intercept, they're really different, but they're both doing a good job on the data set which has been selected for them to train on, right? And so that points to like, well, this is a high variance model because the predicted parameters here can vary a lot from the average parameterization of those models. So is that clear? Does people understand what's going on there, right? So basically, yeah, there's like loads of different ways that you can parameterize the model to give the same result. That's what high variance means. So what can we do about it? We can reduce the capacity of our model, so make a simpler model. Like maybe this model has like all the terms of the input up to like x to the 5 or something. Really, we don't need that. We just need up to x to the 2 or something. So we can reduce the capacity. That is, we can like reduce some terms of the model. We can train on more data points. So if we had data points that were all along this green line, regardless of if we're still going to pass through all of them, then this line will be bound tighter into that green line because it will have to pass through more points which are on the green line. So that's a way that we can get around variance. Just get a bigger data set or train on a larger proportion of the data you have. Again, change the objective function, and also something different and interesting is increase regularization. I don't think I'll go into regularization here, but regularization is basically any technique that you can use to reduce the generalization error, but not really affect the training error. So basically just to improve generalization. We're not going to go into it in depth here, but like one simple way you can do that is basically add a penalty for the size of your parameters. So if you basically add like onto the loss function plus like all my parameters squared, that is, if any of the parameters are large, then they will contribute positively to the loss function. So if we have like an x to the 5 term in this model, then we don't want to let that like overpower all of the rest of the all of the other component, all of the other terms in the model, like an x squared term. So there'll be a penalty on how big each of the coefficients can be. And if the coefficients aren't really that useful, like x to the 5, it doesn't need to be big, then it will be pushed smaller. Whereas x squared, even though having some term in the x squared coefficient will contribute positively to the loss function when you square it, it's necessary. So it will still stay there, even though the x5 will be pushed to 0. Don't worry about that too much, but we have plenty of resources. If you want to check that out, just go to Academy of AI GitHub. Okay. So here's like the summary diagram of that. So what we're looking at is test error against capacity. So that is complexity of the model. When we have like a really low capacity model, so like a linear model, then we're going to have bias in the output probably, because it's not going to be able to capture the relationship that we want between our input and output. That's an underfit model. And so as the capacity increases, the bias decreases because it is able to represent the model that we want. But then variance increases, this green dashed line here. So as the capacity increases, we can begin to overfit our model. There begins to be more different ways that we can parameterize the function that we're using as our model to get a good relationship between the two, between the input and output data. Okay, cool. So there, at the sum of these minimum, at the minimum of the sum of the variance and the bias, we have like an optimal capacity, where it's not, it's between underfitting and overfitting, which should be fine. So below that point, less capable models won't be able to capture the relationship between the input and the output. And above that point, more capable models will be able to, they'll overfit and not generalize. Any questions about that bias and variance? Okay. Cool. So now, so what were we trying to get to there? We were trying to get to parameter estimation. So what make good parameters? That is, we don't want our model to be biased, and we don't want it to have a high variance. They're like the qualities which it should have, right? But how do we actually find them? And the main thing we use here is called maximum likelihood estimation. So, the thing, most likely solution is probably the simplest solution, okay? So keep it simple. That is the best model defined by its parameters, is that which predicts observations that we make as being highly likely. So, intuitively, we're going to make some observations, and then we're going to predict how likely they are, like if we're predicting a distribution, and that's using our parameterized model. And then the best parameters for our model are those which maximize the chance of making those observations. Okay? So, formally, what that looks like is we have some data, like I drew earlier. We predict how likely making those observations are. So go on to this. Okay, basically we have a model which is this P model. So that's just like a distribution, which is just a function, and it's taking in our data set and it's parameterized by its parameters, the weights, theta. And so the probability of our model, how likely our model thinks this whole data set is to appear is given by the product of how likely the model expects each individual item in that data set to appear. It's kind of like more depth than you'll ever need to go into in this, but just to really make it concrete, what you're trying to do is learn a model which maximizes how likely it thinks seeing the data is, right? So if the model you have some distribution of data, you want to be able to look at a new set of data and say, okay, is that likely to come from the same distribution, i.e. is that likely to come from the dog distribution or the picture of cat distribution? And then you'll be able to do prediction of whether it's cat or dog, like that. So basically, we have some parameters, and the maximum likelihood parameters, the maximum likelihood estimation parameters, are those which maximize this term here, that is the chance of seeing this data set. And so you can just like convert that into there by logging it. So have a look at that in your own time if you want. Link for these slides is in the Discord chat. So that's how we can find the maximum likelihood estimator for this model. Okay. And so what that leads to is basically you want to maximize the log probability of each example. So log probability is actually just the log of the probability predicted for that single example. And that's obviously based on the empirical distribution of the data. So you better hope that the data is representative of the data that you care about. Okay. So this leads to, where does mean squared error come from? So why aren't we using like mean absolute error? Why aren't we using like mean quartic error? Why are we using mean squared error? So mean squared error is motivated by maximum likelihood. So say we want to predict someone's height from their age. We can usually tell roughly, but we can't ever be sure because naturally those two things are not perfectly correlated. So so when we predict, how old someone is, what we're predicting is like, well, I'm confident that they're around this age. Like my most likely guess is that they're say 30, but they could be lower, they could be slightly above. And what that means is like you're predicting a distribution. Because these things they don't correlate perfectly, and there might be variation either side. Like we're not predicting a single value, we're predicting like I predict this value is likely, but they could be somewhat older, somewhat younger. And so if our prediction of the ages looks like this, and we ourselves have some model, like this blue line, to predict, okay, how old are they? We'll predict this distribution, and then we'll guess this age, okay? So this age is like the most likely thing we think of. And this is like, if someone asks you, how old do you think I am? This is the number you would tell them here, this mu. But really what you're saying is like, well, I guess, you look like you could be around this age, and I don't know, the spread of that is kind of like, oh, well, they look like they, I don't know, do they have a face which looks like it could be old and young, or is it like their very specific age? And so what you're trying to do is get that to match up with like the true distribution, which is centered around like how old actually are they, and this would be basically the prediction of their age given their face. And so given their face, that x would change. It would change the shape of these, change the positions of these centers and stuff like that. So basically, like we can think of it as a normal distribution, and then using that. Okay, cool. So then using that, we can basically take that normal distribution and put it into our maximum likelihood. So here we just had like, we want to maximize the sum of the log probabilities for each example. Then we could just say, well, the probability, let's model it as Gaussian, put it in there, and then you can work your way through this, and you come up with like, well, maximum likelihood is equal to minimizing the mean squared error, okay? Because this Gaussian has this squared term in, the log cancels the e, and then these other terms are independent of the weights. So what you end up is like, if you want to regress some continuous output, this is the derivation for doing that with maximum likelihood, and that's why you use mean squared error. Ends up with you just want to minimize the mean squared error expected over the data. Okay, nice, cool. So that was the foundational concepts. So just to recap that, we're going to try and learn functions that map our inputs to our outputs. And what that really means is like we want to learn parameters of these functions. And those estimates of the parameters should be unbiased and have low variance. And we're going to train the models using maximum likelihood so that we optimize trading off bias and variance simultaneously. And then if we assume the labels might follow some distribution, like in that guessing the age example, we can have a prior, which is like, okay, I said they came from probably a Gaussian distribution. And then we can try and predict a probability distribution rather than a point. And then learning the best parameters for regression means minimizing the mean squared error. So don't really worry about too much of that maths, which is the derivation of maximum likelihood, etc. Check that out if you want. All these slides are available. But are there any questions about what we're trying to do? Okay, cool. All right, so just have like a 5-minute break, walk around, rest my jaw. Yeah, cool.
Can send us the slides?
Yeah, it's on the Discord chat. You just go to the link I sent you on email.
Yeah, thank you so much.
Yeah, last one. I don't know how specific, but I read yeah, you have like I really want to
Yeah, exactly. They explain exactly what to do.
yeah, so I made it as simple as possible. Did you apply yourself?
Yeah.
Did you do really decent?
Yeah, I was so dumb. I was like, I was working with like, polygon sound. I was like, I'm happy with it. Let's just send it. I hope we reword this bit slightly.
Because didn't you do a draft?
Well, we applied before, so we had that to start from. But we like mastered it, we just changed it.
Did you get free copy?
Yeah, you don't really get detailed feedback on the application. In fact, you get barely any feedback at all, unless you don't get any feedback at all unless you have to interview. You did get to interview, so but then they just like one sentence feedback about scaling issues.
How was the? Did you go over to?
Yeah, mental health. That was awesome.
It's supposed to be really intense.
Yeah, I mean it's like obviously it feels it because yeah, like you flew all the way there for like some of the most yeah, it's like the best investors in the world. So yeah, it's like it seems intense, but when you get there, it's like it's actually not like that. They just ask me questions. They just want to know more about it. It's like really simple. I'm really fucking taking notes. You really get it. Yeah, it's just fun to go out there as well.
Yeah. You get to say something more.
Yeah, we messaged one guy who was Jeff also. And we did like monthly lunches to I don't even think he read them. But like, you know, at least he maybe saw that you was like, oh, it's still out there. Okay.
And you can keep it up to date. So, and if you go through this time, you have to fly over like 3 months or so.
Yeah, that's the That's what I'm
I think you're
yeah, it's like it's really hard to try to find like brand identity, and that's like obviously having the core. Yeah, like I mean like just like color palettes and that kind of stuff.
How important is it just something like
I mean it's not as important as metrics, obviously. Like, but I think like when you want to scale, you need to have something that's consistent to. Yeah, they expect that, but it's not like it's not really like a make or break, I think.
what kind of metrics are you looking for in terms of if you because you say you can like with people in early stage
Just like, I mean, they're looking for outstanding stuff, right? They're looking for companies that could be 10x what's already out there. But that really depends on your company, what you're doing, and what you're doing, like influences, like what actually are the most important things. So what metrics should you be tracking? So for us, it's like conversion rate. How many people sign up and then purchase something? Right. So that's not something we're really trying to push. It's like another thing we're really trying to push is what portion of people who use it are recommended by trainers. And it's like, well, we have banging stats on that. We have like a 60% conversion rate and like 70% recommended by trainers. So
yeah,
that's quite cool.
Yeah. So you can that's what I was thinking. Is it to apply in such early stages like these metrics not really good and specific, or is it worth trying and then maybe go back in? Is it fall?
Yeah, I think it's 6 months. Yeah, it's not that much.
That's something to see. You try and go. You have to keep it up. I must you should keep up on the ground. And follow the journey brings.
Yeah, I'm trying to get more on social media myself. Yeah. I mean, it'd be easy if I just like took photos and put them on there. Yeah, guys, please ask questions. Anything, any single thing is not clear at all.
How can you download the slides?
Can you see the link on the chat,
Uh,
the Discord chat? It's an intuitive way to think about what we actually try and do. If we see some observations of house prices in the real world, and we have some model which we're trying to predict that, what's a good model? A good model says that let's like say what we're trying to predict. We're trying to predict that distribution of the house prices, which I've shown, right? Well, we want the distribution. The model that we have, we want to say, if I show you a true distribution, I want you to say, this is very likely. Right? You get that? Yeah. So, and then what we're saying, like here, so this is like, what's the likelihood of seeing that data set? And that's real data, right? So it's like, well, it should be high, which means you want to maximize that, right? And so then this is just this is just like working through the maths of that, okay? So probability of the whole data set, the probability of individual items if they're independent, and then you can just log that, stability, and maximize the same thing. And then, the parameters which give you that maximum likelihood for that data set you've seen, can be worked out like that. And then if you plug the Gaussian distribution, derive them into that. Exactly.
But like normally we wouldn't use AI for the distribution, it's just using the distribution for moderation.
If you do it was not distributed.
Obviously compare that to the real data is still trying to provide the distribution. That's like, it's counterintuitive to me because you can just order it with normal, if you know it's a normal distribution, how do you know that it's a normal distribution?
Yeah, but it's a question of like, okay, what will we measure? Because we're going to get onto using things like doing computer vision. Like every feature is a pixel. So, is that normally distributed? Like, I mean, firstly, like, it'll be harder to learn, not impossible, but harder. Secondly, like, it's not going to be normally distributed. I'm not going to be able to do it like that.
Yeah.
I'm going to need more complex functions.
I see.
That, right?
That makes sense.
Yeah, so, and it applies in exactly the same way, right? It's just like, the next slide is just like the intuition of why you can think of it as Gaussian when you're predicting a continuous value. This is already predicting a distribution over values and then choosing the maximum most likely one.
Yeah, that's good. Thank you.
Nice one. Alright, let's do this. So if you go to Google Colab and then just create new Python 3 notebook, we're going to go from there. Okay. Cool. Yeah, so today we're gonna do this. We're gonna try a new thing, which I'm really excited about, and it's gonna be a massive challenge, but it will be a real way to learn things, I think. So we're just gonna do this like live, like totally live. Like there's nothing. I'm not reading any script. I'm not looking at anything. We're just gonna try and do it live, and what that means is that this is gonna break 100 times before we get there. And Haroon and you guys are going to help me debug it, and we're going to look at the docs and see what we're doing wrong as we go, and we should then show you like, well, how do we actually program these tutorials when we're not doing it in front of you guys? It's like, and then you guys should be able to use this to go and build stuff for yourself, because this is how, if you don't know how it works, go and look it up, and you can find it. So what we're going to do, firstly, is we're just going to create some data and then look at it. So part 1, create data and visualize it. Okay. So we're going to import NumPy, and what else are we going to need? We're going to import matplotlib.pyplot as plt. Okay. Yeah. So run that. Shift Enter to run a cell in Colab. Raise your hand if you used Jupyter before. Jupyter Notebook. Sorry. Raise your hand if you haven't used Jupyter Notebook. Raise your hand if you've never you've used Colab. Okay, no worries. I just want to say how it works then. Basically, it's just code that you can run cell by cell. So every different part. See, this is one cell. This is another cell. So you can just press Shift Enter to run that cell. It's the same in Jupyter if you ever use that. And you can have different types of cell. So you can have I'm not sure how you do it actually. But you can put like markdown in some cells, so you can basically have descriptions around code, and it's like a really good way to both learn by running it just piece by piece and understand exactly what every part is doing, and like comment it nicely. And so yeah, this is Google Colab. Another interesting thing you can do is go runtime and go change runtime type, and then run it for free on Google's TPUs or GPUs, which is nice. Won't really make a difference here though. So yeah. Okay, cool. So we're gonna first make some data. Okay, we're gonna make some input labels x. So then we're just gonna say np dot. So okay, yeah. To talk about the whole problem, firstly, what we're gonna do is we're gonna make like a load of different x values, and then we're gonna make a function y. So we're just gonna say like y is like x squared plus 3x cubed plus sine x or something like that, and then we're going to plot them and take a look at it, and then we're going to build a model which we'll initialize with random parameters, and then we'll try and optimize those parameters such that it fits the model better. Okay, so I'm going to basically take a number line like between 0 and 100, say, and I'm just going to make different data points like spread out throughout there. So there's a function called linspace. This function linspace, what does it do? It returns evenly spaced numbers over a specified interval. So NumPy linspace start stop default number is 50. So we'll go from 0 to 100, and then we'll print that x. NumPy as np. Cool. So there's our inputs, right? They're just spread out between 0 and 100, and there's 50 of them. And then we'll go, we'll say that y is equal to x, I don't know, let's just say 5x plus 10, firstly. Okay? And then what we'll do is we'll do plt.plot. So using matplotlib pyplot, we can plot x and y. And you see that. So this is our this is the data we've got so far. I should have done it a bit smaller. Cool. Can I set like the x lim and y lim without doing a figure, or how? Cool. So that's more like representative of what we're talking about, right? So yeah, there's our grid, and here is the function which we want to learn, right? That's a really simple function to start with. So now let's build a model. Okay, so the best way of doing this is probably, should we build a class PyTorch model first, or yeah, like the usual. Okay, all right. Okay, so we're going to define a model, which is going to take in our input x, we'll call it input, just to make it even clearer. And then it's going to return, let's say, is equal to, so we're going to have some, so we'll say, the weights is equal to np dot random. So we'll make a random array of size 2, and then the output is going to be np dot matrix multiplication of the weights with the input. Okay, and then we're also going to have the bias, which is going to be np dot random a single number. Sorry, we only need one weight. Yeah. Yeah, I think so. Okay, yeah. So just to like highlight this, like what we would be doing here though, like here would be our model, right? We define a function, like literally a programmatic function in this case, which takes in our input. We get some weights, which are just these random numbers to start with, and then we initialize a random bias as well, and then we're going to output the multiplication of the weights with that input, and then we would add a bias. Okay, and then we would return that output. Okay, but that's not really going to do anything, right? Because we need to initialize those. We need to basically be able to update the weights and set them to something useful. So what we'll do instead is we'll build a class. We'll call it model. And then we'll say, okay, when I build this model, when I initialize it, I'm going to call this constructor by default. This model is going to take, okay, how many features does it have? That's what I want to know. And then number of outputs. that's another thing that I'm going to want to know, because when I build this model, I firstly want to randomly initialize the weights. So I'm going to say, if anybody's not clear on any of the code as well, like if you're not sure what a class is, if you're not sure what I mean when I type self, just ask. And okay, yeah, so we're basically going to say, well, this instance of the model's weights are equal to some random initialization of, they're equal to some random numbers. And how many numbers do we need? Well, the number of features that we have is the number of weights that we need as well, because we're basically going to just make a linear model first. So we're going to weight each of those features by one number. Those numbers are going to be the weights. So we'll make features.
That should be like parameters to the function, not the class.
Oh yeah, sorry.
Also, np.rand and.
Oh, is it? Okay. So yeah, that goes to NumPy's random library and then gets you random normally distributed numbers, that rand_n. So there we've got our weights, and we'll say self.bias is equal to np.random.rand_n, and this is just going to be, this is going to be number of outputs. So how many biases do we need? Like how many outputs do we have that we need to offset? Well, just the number of outputs there. Okay. So we've defined like what happens when we start this function when we create a model, right? So we create if we do this down here, my model is equal to an instance of model. Usually, let's do that. We'll create a model. So when we do this, when we run this line, what's going to happen is it by default calls the constructor. So it will set the this instance of the model's weights and biases to random numbers of the right dimensions. Okay, is that clear to everybody? Oh yeah, cool, thanks. All right, so we've set the model up. Now what we want to be able to do is pass things forward through it, right? So we'll say def forward, and this will be the function which takes in our these need a self, and so do this one. They will take in the input, I'm just going to call it x there, and then they will return the output. Okay, but what is the output? The output is defined by whatever we make the model, right? So what we'll do is we'll say that output is equal to np.matmul so we'll do a matrix multiplication of self.weights with x, and then we'll add the bias. Okay, then we'll return the output. So okay, so we can delete that. Right, and then we can say, well, now let's make some predictions, and this is just going to be awful to start with because these are just randomly initialized, right? So we'll say predictions is equal to, what's the best way of doing this? So we'll make a list. And then we'll say for example in x, that is every element in x, we will get the model and we'll pass that data forward through the model. And then that will return us prediction. And then we'll do then we'll append that to the prediction. Yeah. Sorry.
You just matrix multiply the whole thing instead of appending to predictions.
But it's going to have to pass the. Oh no, yeah, you're right. I can pass the whole thing into that, can't I? As long as the dimensions are right. Yeah. Okay. Cool. So, yeah. All right. Let's try this then. I haven't used basic NumPy in so long, so that's what's happening. My model dot forward. So we'll pass all of the data through that at once, and then we will plt dot plot predictions, and then we'll plot those predictions against the x, and then we'll plot our x and y again, and then we'll see what happens. So yep, didn't initialize that with number of features, and yeah, so I didn't pass in the features and the outputs, so it's just 1, 1 in this case. Shapes 150 not aligned. Sorry? Oh yeah. Good shot. Okay, so yeah, we won't do a multiplication, we'll do a dot. Run that. Okay, so 50 and 1 not aligned, so I'm trying to do a dot product of the weights, which is one-dimensional, and the features, which have 50 dimensions. So how can I do that? So we can look up broadcasting p multiplication. Actually, wait, hang on. I think what you just be able to do is sorry.
Expand bins on the x, so it's 51, 50 common.
Okay, yeah. So we'll say is x dot reshape. So reshape that to tuple can not be as interpreted as an integer.
Yeah, the x dot shape is a tuple.
Yeah. Okay, well firstly let's just like print
Do -1 common.
oh yeah, good idea. So we're going to reshape the x so that it has as I don't care how many rows, that's what -1 means, and it just has 1 column. And then we will multiply them together as well. Self.weights with x.
If you make your weights 1, 1, then you probably...
Hang on, do we even need to do a dot? I think we can just do a multiply, right?
Yeah. No, like NP dot map all. Because that will do, try and do element.
Is that not going to work? Yeah, there you go. Right, yeah, so sorry for all that confusion, but you can just, so what we've got we initialized some random weights. That looks too good to be true. So yeah, we initialized some random weights, I think, we'll check it in a sec, and then we initialized random bias, and then we passed that forward. We just did the weights multiplied by the x plus the bias. And so what we've done here, like this is just a scalar, this one, right? Because we've just given it size 1, that is n features is 1. And this bias is just a scalar as well, which is, again, size 1. So what we've done here, we've multiplied a number, which is a scalar, with a vector. And so what that's done is it's broadcasted the multiplication over the whole vector. So really we've multiplied every element in this vector by this weight, and then added the bias to all of those. So when we start it up, just to check what's happening, let's print self.weights, and then print self.bias. Run that, yeah, so there you go. That was conveniently good, the first one. So here's a random initialization, right? The green is our true data, we know, and the blue is our model to start with, right? So these are our this is our weight to start with, negative 0.3.5. So that's the slope here. It's going downhill by -3 every time we take a step. And then we've got an intercept of negative 0.31. Okay. So now we need to make it slightly better. All right. Any questions so far about what's happening? Okay. Cool. Don't need that anymore. Cool. Simple as that. Simpler than I even thought. So now what we're going to do is we're going to try and build some functionality to update these weights. All right. So we're going to need to build a loss function to determine like how bad we're doing at the moment, and then we're going to build a function to return us the derivative of that, and then update the weights. So let's just think about what the best way to do that is. So we're going to need to calculate the loss, so we're going to need a function for that. So we'll build here a function loss, and the loss function is a function of the predictions and the labels. And what it's going to do is it's going to take the average square difference of those. So we will do loss is equal to predictions minus labels. Now we could do it squared like that. You could also why does it do that? It's so annoying. Predictions. Cool. All right, predictions. Yeah, so we'll just do that, to be honest. So we'll take the square difference and then we'll average it. So that's taking the square difference, and then we'll do loss divide equals by. So shorthand for loss equals loss divided by predictions dot shape 0. So shape returns a tuple. So thanks. Just check that. Print shape. Print predictions dot shape. We can do that. Right. So now we have some predictions, and we have the label. Now let's get the current loss is equal to. Well, that's not going to work, is it? If I So we'll call this loss underscore function. Oh god, so annoying. Why does it do that? Okay, so we got loss function, and then we'll have that return us the loss. So we'll do loss underscore function of the predictions and the labels. Loss function predicts labels, print loss. We'll run that. See what we get. Labels is not defined. No, it's not, is it? So our labels are our y. Invalid syntax, really. Okay, cool. So, I guess, is that meant to be the loss? So that's the loss for, as apparently what I've returned as the loss for all of those examples. But I think what that is the, is that we squared, so here we squared all of the, we squared the difference between each prediction, and then so this is again, this is a vector of 50 numbers, and so is this. So then the return of this is a vector of 50 numbers, and then we're just dividing all of them by that shape. What is the shape? Just to check it. So yeah, it's 50 like that. So we've divided all of them by 50. So if we didn't have that, we'd get much larger errors, right? Much larger loss. Yeah. Again, like if I don't make clear what I'm doing at any point, just shout out and ask, or yeah, Haroon, do the same if you think I don't do something. Okay, cool. Yeah, so we can do here. We'll just sum up all of those. We'll just sum up that vector. So we'll do np.sum pr predictions. There you go. Okay, we'll run that, and then this is our loss for this current like batch, but this batch is the whole data set here. Okay. Right. So we've got our loss function. Return the loss, and okay. So now we're gonna basically, we want to know what's the we want to be able to return the loss, and we also want to be able to return the gradient of the loss. So what I'm going to do is I'm just going to make a flag in this function called gradient, and we'll say by default it's false. What I'm going to do with this is if I'm going to say like if I call loss function and say gradient is true, then I want it to return me the gradient rather than the actual loss. Okay. So we'll do if grad. So if gradient's true, i.e. if I want it to give me the gradient, then I want to, you know, here return the grad, right? But then not the gradient, well, the gradient. But then what is the gradient? Okay. So the gradient is the derivative of that loss function. So that is the that's the derivative of this. So we got our loss function. L is equal to so average over the mini batch of the prediction minus label squared, right? But what we want to do is find the derivative of that. So we want to find rate of change of the loss with respect to our weights, and that is a function of our weights. Okay. So what is that function? Currently, this y hat is equal to the weights times x plus some y's. So the rate of change of the loss with respect to those weights is the root of this. So 2 over m sum over m I equals 1 multiplied by the inside of that, which is y hat minus y, multiplied by the rate of change of this with respect to this, which is x. Okay. Correct me if I'm wrong, but I think that's right. Yep, cool. All right. Okay, cool. So now that's what we're going to return if gradient is true. Okay. So we'll do gradient is equal to 2 over m. Actually, we'll just divide the final thing by m. So we'll do 2 times np dot sum. So literally, like, this is me just like reading that equation and trying to implement it in code. And I think like this is like we were saying the other day, like this is like one of the most important things where people kind of have the gap of like, okay, I know the theory, okay, I can code, but how do I convert it into actual Python and then run it? All right, so just reading it out, like it's got a sum in there, so I do np.sum. The sum is of the difference between the predictions and the labels, and then that's multiplied by So we also need the inputs in this case, don't we? So then we'll add another thing. We'll say features equals none by default because we don't need it for the part which isn't grad. Just spread this out for clarity. So then it's going to be multiplied by the features. Okay. So.
Question. Where is it? Predictions, comma labels.
Yeah. No. Sorry, that's wrong. You're right. Cheers. Oh, why does it do that? It's so annoying. People see what it's doing. That's annoying me. It overwrites the next letter in the in the line.
Press insert.
Sorry.
Press
Insert. Oh, is it?
insert.
Oh my god. I never realised that's what that was. I don't think it is.
Press it again. Maybe you need to press the function button too.
No, I am. If I don't press the function button, it's a print screen, I think. Maybe. No, yeah, there you go. There you go. I don't know what that was. All right, thank you. I never knew that's what that button did. So, minus labels. Okay. I lost what I was doing. Okay. The sum of the predictions minus the labels. That doesn't need to be there. Multiplied by features. Okay, right, that's what we want, isn't it? Divided by m. Okay, cool. 2 over m multiplied by the sum over those things. Difference between the predictions of the labels multiplied by the features. Cool. Yeah, cool. All right, now we should be able to. So,
The bias, right?
What-
You need to expand that where you separate weight, bias, and then
yeah, I need the bias as well. Is that what you're saying? Yeah, cool.
take the gradient respect.
Yeah, cool. So yeah, Haroon's right. So this model has 2 parameters, right? It has the weights and it has the bias, and we want to find out how to change both of those, not just the weights like I've done there. So we'll also have to differentiate with respect to the bias. So I mean, all I've done here is this is rate of change of L with respect to y hat, and then this is rate of change of y hat with respect to the weights, and in the same kind of way, calculate rate of change of loss with respect to the bias. We would just do rate of change of loss with respect to y hat times what rate of change with the prediction with respect to the bias, which that is that, and then this is the rate of change of that with respect to the bias, which is just 1. So it's just this. So we get 2 over m, sum over m, I equals 1, y hat minus y. That's what we're going to do. All right, cool. Any questions?
Did we define M?
Sorry?
Do we define
So we haven't defined m, but m is the m is like the number of examples in this batch. So that's the size of this predictions, right? So by summing over m, we'll just divide by. You're right. We need to divide by that there. So that m is the prediction, is the shape of the predictions, right? So yeah, we'll just put that here. Thank you for that. So we'll say m is equal to predictions dot shape 0. So remember that predictions was a tuple, and we'll just get the first element from that tuple, and then we'll divide by that m there. Okay, cool. And so yeah, when we're summing over these things, that's the sum over m because there's m elements in those 2 vectors. Okay. Cool. So, what are we doing? Yeah, we need to return the rate of change of the loss with respect to the biases. Gradient. So that's the gradient of the weights. And then we'll have gradients of the biases is equal to that. It's the same thing, it just doesn't have that features there because that partial of the prediction with respect to the biases is just 1. So, okay, cool. So we'll return gradient of the weights and we'll return gradient of the biases. That should be good now. And then we will we'll get our grad W, grad bias is equal to loss underscore function of the, so it takes in the predictions, it takes in the labels. In this case, we're going to say grad equals true, and then we're going to say, in that case, we also need the features is equal to x, okay? And then we will print the gradients of the W. See what happens. Seem to work. Cool, right, so here, that should not be that big, should it? Yeah, okay, cool. So it's gone through and it's returned us this this apparently vector of gradients and this scalar of bias gradients. So yeah, this. Okay, let's see what's happening, right? Because it shouldn't be returning us a vector of 50. It should just be a vector of 1. Okay. So what's happening here? We're doing.
You need to times it by features before we sum.
Yeah, you're right. I think so. There we go. All right. So now we're getting somewhere, right? So we've set up the model. Here's the initial weight. Here's the initial bias. Here's the shape of the predictions. Here's the total cumulative loss. Here is the rate of change of the loss with respect to the weight. Here's the rate of change of the loss with respect to the biases. Okay. So now we can use those things in a gradient descent algorithm and just so do this update rule. So basically, gradient descent just works by like do this thing on repeat, take the weights you have, set them equal to what the weights currently are, but then move them in the direction which decreases the loss, respect them in a small step size, and that's the learning rate. Okay, cool. People understand what that means? Oh. All right, so now we'll have another function in our model. We'll say def step, maybe update weights is clearer, or maybe update params is even better. So we'll update the parameters of the model, and what that will mean is we will take in the gradient of the weight, and then the gradient of the bias, and then we'll just do that. So we'll do self dot weights subtract from. So subtract from the weights. We'll initialize a learning rate as well here. So we'll say self dot learning rate is equal to 0.1, let's say. So our steps are going to be 0.1 times the gradient. So we'll do minus equal to self dot learning rate multiplied by gradient of W. And then we'll do self dot bias subtract it from, so subtract from the bias, the learning rate multiplied by the gradient of the bias, and then here we should add a default. So there you go. Now, if you write this, you can just change the learning rate of that model when you initialize it. Okay. So now, what we're going to do? Is interactive plot going to work? If I make a figure, maybe. What is it? What's the command?
Right at the top.
Yeah. Like that.
Yeah, yeah.
Cool.
So this just makes it so that you can run interactive plots in the
Okay. So, all right. Now we're gonna make like a training loop, I guess. So, yeah. So firstly, what I'm gonna do actually, do I have to make a figure, right? Figure in an axis and then update the axis. Yeah, cool. So yeah, just to make the visualization like a bit more solid, we're gonna do we're gonna create a figure. So we're gonna do.
I don't know if it works on Colab. It works on normal
Okay.
groups, no, but I don't know.
All right. Worst case, we're just gonna look at the loss and hope it goes down, and then debug until it does. Okay. So we'll do. Right. So we're gonna put this loss function evaluation in a training loop. So we're gonna say. Yeah, we're going to say for epochs in range epochs. So an epoch is a run through of the whole data set. So this is a hyperparameter of the training where we can just say, okay, how many times we want to go over the whole data set? And so we'll say like, okay, let's just go over it 10 times to start with. So this range epochs gives you like a range object, which is basically like a list of numbers up to 10. So, and then it's going to go through this that many times. Yep, we'll do the loss function like that, and then we'll get this line, get that there. Okay. Okay, cool, right. So basically we're just going to go over the whole data set, and we're going to evaluate the loss function, we're going to get the gradients, and then we're going to use those gradients to update the model, right? Yes. Okay. All right, cool. So here is like what like a more solid training loop is looking like. So we'll make some predictions. We'll plot them, and we'll plot our labels, and then we can do like this will work, won't it? plt.clear. Clear axis, clear figure. Is it not going to overwrite this one though? Because I've just done plt.plot twice and it's printed that, and it's plotted the thing twice. Sorry, it's only plotted the thing once and it's put 2 lines on it. So I'm just worried it's going to just keep going and putting more lines on the same plot. You might be able to tell the difference.
Yeah, but if you do plt.fig,
plt.fig.
yeah, so it keeps on the new figure.
Oh, okay.
So at the top.
Yeah. All right, cool. So, yep. we'll make some predictions by passing all of the data set through the model. Then we'll make a new figure. We'll plot those predictions. We'll plot the relationship that our model is representing. We'll get the loss for that current model. Then we will print the gradient of the loss with respect to the weights. Then we will print the gradient of the loss with respect to the biases. And then we will do update underscore params. And what does that take in? We said that takes in the gradient of the weight and the gradient of the bias. So grad underscore W, grad underscore B. All right, so, and then we'll also just print the my model dot weights, and we'll print the bias. All right, let's run this. We'll also print print the loss. And then we'll just print a new line. All right. Update params takes 2, but 3 were given. Yep. Cool. All right. What's happening? Doesn't look like it's working. What?
Wait, go to the top, rotate like all the way to the top, do matplotlib inline instead.
Is that the latest one, or what?
Yeah, so do PLT dot figure.
Cool, right, so here is how our model changes over time. Pretty bad. Goes straight to 0. Sorry?
I think you need to slow down.
Yeah, me too. Yeah, what's probably happening is we're getting pretty high gradient, which is, yeah, we're getting these kind of things, and like then our optimization step is taking is moving the parameters by our learning rate multiplied by that. In our case, we set the learning rate to 0.1, so it's going to move the weights by 800 in the other direction, right? That's not what we want. We want it to move more like 0.8. So let's set that to. So let's set the learning rate down to a much smaller number. Then we'll see what happens. Okay, come on. All right, something is happening. There we go. That's looking better, no? So let's run that for hella more epochs and just see what happens. Doesn't look like it's getting much closer as we go on.
What are the gradients?
Yeah, let's have a look. Yeah,
Yeah,
because it's much smaller. So
the update.
yeah, should we set different learning rates for each one? Or?
I don't think it's even that. I think it's just not updating the way the value is
Okay.
changing at all.
Yeah, you're right. Okay. Right, update params. Self.bias. Nah, it is. It's just really small. But that's because they're on different sizes, right? So we get this, the gradient for W is what I looked at first, and I said, okay, we don't want to take step size that big, or even 1/10 of that. We don't want to move it 200. So I said, we'll take like 1/10,000th of that, so we'll move in like 0.2. But if we're using the same learning rate, then we're also dividing this by the same number. So then that, because these the gradients for the loss are much smaller, the gradients for the bias are much smaller. They are it's not moving enough, right? So as you'll see soon, like we can use like much more advanced optimization techniques, much more advanced optimizers by using like pre-built libraries. Like I don't want to build one in NumPy here, to be honest. So we'll get onto that in a sec. But just for now, like something we can do probably is we can set this update. We can do like 100 times the learning rate for that and see what happens. Actually, let's stop that. Don't want to run it for that long. Don't think I needed it. So we'll just run this for 10 again and see what happens. Okay. Okay, a bit larger. Strange. So this bias here, right, should be getting closer to 10 because that's what we set it at.
Could be grade clipping.
No, it's moving in the right direction now. I think it just hasn't gone for long enough. Let's try it for.
Maybe you should take random samples from the data and serve the whole thing.
Yeah. I don't know if I can bother to implement it now. Just move on to neural networks and start doing a PyTorch implementation, I think.
This part.
Okay. Alright, what's happening? There you go. Yeah, cool. So, everybody understand what the problem was? Basically, the gradient was smaller for the bias than the... yeah, it was smaller, but that's not really the problem. The problem is that the... yeah, well, that's another problem. But well, okay, yeah. So basically, the problem was that the gradient, the rate of change of the loss with respect to the gradient, the rate of change of the loss with respect to the bias, were on kind of different scales. So when we're taking those gradients, multiplying them by a learning rate, and using them to update the model parameters, we need to be taking different relative step sizes because they both need to go from like around 0 is where we initialize them to around so what did we set this as? We actually set this as the gradient was 0.2 and the offset was 5. So maybe if those two things were on the same kind of scale, like maybe they were both 10, whatever, then we wouldn't have needed to do that that manual augmentation of the learning rate there. But yeah, that was basically just to put them on different scales so that in the number of epochs that we're doing, they both converge fast enough and we can get like a good enough model like that, right? So let's make this slightly more complex first, right? So let's add like an x squared term. 2 times x to the power of 2. And then we'll run that. And see, our model is still linear, right? But within this range, like, that's a good fit, right? So this is a case of what we said earlier about this is an underfit model because it's not capable of representing that that function, but that is the right function, right? That is the best function that a linear fit could give to this data. Like, for some reason, if you wanted to model it so simply. So here you can see it goes up. You know, it gets it right pretty much straight away based on the step size of the updates. Yeah. Okay, cool. Everybody clear what's happening there? Any questions so far? Anything? What's going on? All right. So now let's add. I don't know if we want to do that. So what we could do is we could add in more complex. We could make the model more complex, right? So we can make the forward function not just be weighted combination of the inputs plus the bias. We could also add weights for, we could say like these like self.linear weights, self.quadratic weights. We could add or something like that, and then we could take the features and do something like this. We could do like self.quadratic weights times x squared, right, like that. So we could just add a quadratic term into our model like that, right? But then we would have to write, we'd have to write another rule in the updates. We'd have to write another initialization function in here, and it just quickly gets out of hand. Particularly if we want to start solving like interesting problems, right? If we want to start doing computer vision, we need really complex functions to represent that, and it's not going to be, it's not going to be a quadratic fit. That's certainly not going to be able to do facial recognition. We're going to need something way more complex. So now we're going to move on to talk about neural networks and why we use them, what they can represent, and then we'll talk about PyTorch, which is a computational framework for deep learning, which means that we don't have to write all of this stuff. We don't have to do any of it by hand. It's all just taken care of in the background in a really efficient way. So we will leave that there. Like, has everybody been following on? Cool. So should I send this out later? People want that? I'll do that. Okay. So yeah. Cool. All right. Now let's go back here and talk about neural networks, deep learning. So we takes forever to load. Okay, cool. So we did some machine learning. We know what that is now. We talked about the things we need: model, data, criterion, optimizer, and then we implemented them in code and used stochastic gradient descent along with a mean squared error to optimize a linear model. Right? Using that code that we've already written, it wouldn't be too hard to implement, like more complex models, add more weights for different terms in the model, like quadratic terms, etc. You can add whatever different terms you want into that model, Gaussian sign, etc. And feel free to play around with that. Feel free to try and break it. Feel free to try and find out what doesn't work, and just play around with it. So yeah, the point, what we got to was we wanted to build a more complex model, and we would have if we had more time. But we don't actually need to, because we can use computational frameworks to build it for us. But the question is how do we know what terms to give our model? We want to be able to, we don't want to We don't want to bias our model by saying like, okay, yeah, cool, you need to have a quadratic term. Okay, you need to have a sine term as well. We really just want it to be able to build whatever function, build a general function. So that's what we're going to use neural networks for. So I should just follow my slides and it will explain that in a better way probably. Okay, so useful input-output relationships are too complex to guess what model might fit them. So it's not going to be like, that one, just like the one we were looking at then. It's going to be more like this, right? And this is only in one dimension. If this is a computer vision problem, we've got 1 million pixels in an image. That's in a 1 million dimensional input, which means that there's not just one input axis, there's 1 million. And it looks like this in every single different direction, okay? So they're super complex functions that we want to model, right? And assuming any particular function as the model makes it biased. So like, yeah, here, like we could have a sine term in the model, we could have a high order polynomial, we could have a Gaussian term, but assuming any of them is kind of like, thinking we're better than we are and thinking that we'll be able to see, okay, cool, I know that I can, I'm going to guess that these images of dogs, the pixel in this position is distributed with a Gaussian, etc. So how can we hope to guess a function that will learn a sufficient model? We need a model to be able to fit any shape. So yeah, just to motivate deep learning, talk about the curse of dimensionality. This is a problem which is the fact that as the number of dimensions of a problem increase, there become exponentially more possible states that each example can take. So with more possible states, we need more examples to cover the space. So you'll see that here. So basically, like, imagine every feature. In this case, we've got 5 features. It's kind of just like a made-up diagram, so don't worry about it. But 5 features, and they're all binary, right? They're either like, yes, it has this feature. No, it doesn't have this feature. Blue means yes, let's say. So it's like there's one feature, and there's 5 different possible values for that feature. Okay, right? So in this case, like, well, here's one example, right? It has value 3 for feature 1. That means, and if we have a label for this value, like say it's like, okay, if it has this feature, it's a picture of a dog, then we know, okay, when we see examples like this, we know that the label is dog, right? And then there can only be 5 different, there's only 5 possible states in this whole space, right? It's going to be blue in one of these positions. And if we have 5 examples, then we can look at those examples, and any new examples which come up, which are going to match one of those examples, we can say, well, I've seen the label for that before. That's the new label I'm going to give to this one when I do inference and predict my actual output for it. Okay? So that's, it's a very simple feature space, right? It only can take 5 possible values, and there's only one feature. Well, now what if we have 2 features, and they can both take 5 values? Well, now we need, now there's 25 different states, right? So we would need 25 different examples, like those blue examples there, to know what happens at every point in this space. Okay, and if there's 3 different features, each of which can take one of 5 different values, then we're going to need 5 cubed, so 125 different examples, and we need to make sure that they are all different, so that we've covered the whole space, right? And that means that we know what happens at every, what happens. The ideal function which maps input to output, we know what happens for every input because we've seen every input, right? But again, right, like if this is this is increasing exponentially, and if we have 10 features, which isn't a lot of features, right? Like you can think of more than 10 features for a house if you wanted to predict house pricing easily, then you're going to have 5 to 10 different states, and that's like way more houses than you're going to be able to go and get that data for, right? If it's a computer vision problem, then you can have millions of features. And that's way bigger than, actually, I don't know what the biggest data set is right now, but there's a hell of a lot of images, and the more resolution you want to get to, the more you increase the feature space, which means the more examples you need to know what happens to every example when it goes through your model. So because of that like high dimensional problem, what we want to be able to do is abstract from that low dimensional data and say, okay, well, even if there is 1 million different possible like permutations of an example, then I want to say like, okay, well, let's just split it into 10, and I can classify those 10 different things as like 10 different classes, let's say. So you want to abstract from the low-level data to build up, to group things into like a higher-level representation of them. So just walk through that. We don't pay attention to every raw input. We abstract from low-level features to high-level features. So every photon that hits your retina, you don't see that. You see a holistic object, right? We don't hear that, low-level frequency and amplitude over time. We hear a voice and we know what it means, right? We abstract from that low-level data. Touch as well, you just feel something, and it's like, okay, this is, that's so simple to us, right? I can hold the apple in my hand, and I can just be like, that's how I can describe it. Yeah, it's just the apple in the hand. I don't need to describe the location and pressures each point on skin. So, and that's like what means we can deal with these super complex environments, right? We know what to do in all these actions because, everywhere I look, every one of us, we're seeing something we've never seen before, but we can generalize by abstracting that to something we have seen before, which we know how to act on. So, forming abstract hierarchical representations of low-level data alleviates the problems of the curse of dimensionality. And so we want our models to be able to make abstractions. And we're kind of like moving away from like, a linear, just a straight line now, to how can we actually solve AI problems, which are about modeling complex transformations. So, so the function the model we just made, the linear model, that was applying a single transformation to the data, just an affine transformation, a linear transformation, and then that was the output, right? But really, we want to be able to model nonlinear relationships, and we don't want to bias the model by saying, okay, cool, have a quadratic term, have a cubic term. So we can represent complex functions by repeatedly applying simple functions. So this is the linear model that we had before, right? So we have, let's say we had 3 inputs, and then we have obviously 3 weights for those things. So each of these arcs represents a weight, which each respective input is multiplied by, and then they're all summed into this output here. So this is a linear model where just a weighted combination of these inputs by these weights equals the output prediction y hat. And this can be put in matrix form like that as a single transformation, a single linear transformation. But if we want to model complex transformations, then we can basically just apply lots of small, simple, single transformations to build up a more complex model, right? So what's happening here is like we had our data, and we made a feature from it as a weighted combination of the inputs, right? And that feature was, in this case, that feature was the actual output. That was what we took as the label. What we took as the prediction. And so we want to be able to and so what we're doing when we like make transformation on transformation on transformation, what we're doing is we're just building features as we were before. So here's the same feature, right? But then in the next transformation, we're building features from those features. So we're building on top of what we've already extracted from the data, right? So this input layer here is like, that's the really raw low-level stuff. That's the pixels in the image. And then from that, we might be able to say, okay, well, it's like it could be any example. But like, okay, cool. Here's how stripy the image is. Here's how present like diagonal lines in the image are. Here's etc. And then from those slightly more complex, those features which are slightly more complex than the raw input, we can build features from them. So given how stripy, diagonal lined, like whatever spotty the image is, we can combine those to build more complex features. And these can be things like, okay, well, if it had, circular pattern and dotted pattern, whatever, like then it might be like, well, it's more like a face, right? Circular face. And this feature here might be like, okay, is there a face there? And then we can do more prediction on top of that, right? So basically, what we're going to do with deep models, which we'll explain like more comprehensively in a sec, is like build features on top of features on top of features, and so on until that we have something which represents the abstract complexity which we actually want to be able to predict. Okay. So in that case, we've done 3 transformations where each of these layers is just a weight matrix. Each of those arcs, again, is just an element in that weight matrix. And we've used those to make a more complex function. However, it's not quite as simple as that, because if we repeatedly apply linear transformations, they can be like factorized down into just single linear transformations. So there's like the full map of this, deep, as shallow as a deep model can be, a 2-layer model where we build features, these z-scores from these x's, and then we build a prediction from a weighted combination of those more complex features. Here's where all the weights are in the model. And so then you can, this is the function which that represents. That is equal to this, so just taking that weight, multiplying it by this weight, multiplying it by the input. Well, then you can just, you can multiply these two out into one matrix, and then it just becomes a linear model again. So even though you added the complexity of, initializing these extra weights and doing all this extra multiplication, extra computation, you may as well not have, and you may as well have just, used the original weight matrix and then learnt these weights, because these are just numbers, right? These are just numbers there. And so then the model decomposes to that. So we want to prevent that, right? So we use activation functions. What is an activation function? It's simply a nonlinear transformation that we apply to each input of a hidden node. So just to get that terminology back, these are all input nodes, so they're like inputs to the model. These are hidden nodes because they're in between the input and the output. Hidden layers, consist of hidden nodes. This model has like 3 layers, 1, 2, 3. What other terminology? You might call these units or nodes. The nodes in the input layer just represent the input values. The nodes or units in the hidden layers represent activations of certain features present in the data. Okay. So I think we'll talk about that in a sec as well. So activation functions are nonlinear transformations that we apply to the input of each hidden node. So instead of taking these values, these z-scores, as being just like the weighted combinations of the inputs, so this one would be w1 times x1 multiplied by this weight times x2, then what we do, instead of just taking that linear combination, we apply some nonlinear function to it, right? This g. This g is an activation function. And it's just some nonlinear function, right? It's just any nonlinear function, really. Because when this happens, now the function that this model represents looks like this. And it can't be decomposed, because you can't multiply out these 2 weight matrices to form another linear combination, right? It will still have nonlinearities in it. Which means, you can do more complex nonlinear transformations on your input data to get a prediction. So as I said, that's that. And so here we're just saying like A is G of Z. So originally it was Z in these nodes, and now it's G of Z, which is just activated input scores, which is some nonlinear function times the weighted combination of the inputs to that node. Everybody clear with that?
Sorry, why do we need to transfer from linear to nonlinear?
Well, you want to be able to represent complex functions, right? And those functions, they're not going to be linear. Anything interesting is not going to be modeled by a linear function. So we had the idea. Okay, cool. Let's build features from features and do that by repeatedly applying simple transformations. So we can use the same simple transformation as a tool to build something complex. But we can't do that if we don't have an activation function, because we can just multiply those 2 matrices, W2 and W1, to form another matrix, W3, which again is just a linear transformation, right? So if we put this G in the middle, you can't multiply them together, and the output then represents a nonlinear transformation. Does that answer your question? Cool. Okay. So, activation functions. What functions do we use as activation functions? You can use any nonlinear function, honestly. There are so many that work well enough that it's not interesting to think of any new ones. So don't think you're like doing next level research by using a Gaussian or something. So like the most common, not the most common. Okay, one activation function you can use is a sigmoid activation function. Looks like this. What it does is it takes any real number and maps it between 0 and 1. It's useful because it's simple, but also because you can use it in like output layers if you want to output a probability, for example. If you have any output and you put it through a sigmoid, it will end up between 0 and 1. So you can represent it. You can have it represent a confidence of something. Say a class classification: is this a dog or not? Another one very similar, in fact, just a transformation of a sigmoid, is tanh. Not really used so much, except in particular cases like LSTMs. But don't worry about that. Just another nonlinear function. The one which is by far most used is the ReLU. And this is the simplest one you can think of. So ReLU, rectified linear unit. What it means, or what it does, is it takes in an input, any real number, and if that input's less than 0, it will return 0. If it's greater than 0, it will return that number. So it's like, it's so close to being linear, but it's not, because it's got this kink in the middle. Yeah, it's just really simple. So all an activation function needs to do is add nonlinearity so that we can learn nonlinear mappings. So basically add nonlinearity so we can't multiply those matrices to decompose it to a linear function. Okay? Again, all of these slides are available online on the Discord chat. If you can't find them or you don't know where they are yet, just put your hand up, ask me or Haroon. Okay, so yeah, as I said, activation functions that perform comparably to the best ones we know are so common as to be uninteresting, because it just needs to add nonlinearity. So just use a ReLU. So now let's talk about the neural network in depth. How does it look? So here is a 4-layer neural network. I'll just describe the anatomy of it. So a 4-layer neural network. The first 2 layers have 4 hidden units, and the third layer has 3 hidden units. It has 2 inputs and a single output, and it's using a ReLU activation function. Okay, this input to output model represents this function. So we'll walk through that here. So we have a first weight matrix where basically the indexing in the matrix works by like the rows are which output does it go to, and the columns are which input does it come from. So for example, weight 3.1 goes to the third unit from the first unit. So that's this line here, right? That's the weight along that line. That is how much does this input contribute to this output. And again, there you go. So out by in, that's 4 by 4. So we're taking those this matrix, we're doing multiplication of this, we'll get the scores in here, and then we'll activate them. So those z's that come in are w1x, multiplication of these two, and then we activate each of them by applying a ReLU to every element in that node. Okay. So, and then we do the same again here, just again matrix multiply, activate them with the ReLU. So again, take the linear combination in each of these nodes and just pass it through this activation function. Okay. Again, like that. Right. Cool. That's like the very low. That's as low level underlying mathematics as it gets with neural networks. So that's exactly how they work. Cool. So yeah, there we go. That's all the stuff I said. Transformation from input to output. And these neural networks can be trained to model any function, no matter how ridiculous, but they just need to be deep and wide enough to do so. Okay. So a simple demonstration of universal approximation, so that you believe me that neural networks can represent any function. Basically, imagine we've got a ReLU activation function in a model, right? And we're trying to model like this crazy function with a neural network. Well, if we look closer, we can split it up into like a piecewise function, right? And if we look even closer, we can split it up into like, okay, yeah, it's just linear parts of it, right? So then the way we can implement this with a neural network is just by saying, oh, the hypothesis output there is this. So what's happening here is like, at this point x1, it's getting a bit steeper. And at this point x2, it's getting a bit more steep. So we're adding some, some weight against the input, such that as the input increases, it increases by an extra this much as it goes up. So the way we can do that is like, so if we have relu x minus x1, when x is greater than x1, this will be positive, which means relu will output that positive number. When x is less than x1, this will be less than 0, which means relu will output 0. Okay? So when x is less than x1, there will be no contribution from this term to the output, right? Because this relu will be 0. But again, like when x is greater than x1, then this thing will be positive, and then it will contribute to this hypothesis. How much will it contribute? Well, that's dependent on this weight here, right? This would just be like a weight in like one of the final arcs in the neural network, and then this would be the bias in a node which leads to that unit, which then is multiplied by that arc. And then when it gets to that penultimate layer, it's applied with relu. So it's either like, is it on, is it not, and is it going to contribute to the output by that weight? And then we can go along, and as we get to x2, the same thing happens. So if x is less than x2, well then this term is not going to contribute to the output, right? But as it surpasses that, then we're over here, then we're having this extra gradient, this extra extra contribution to the hypothesis added. Again, the relu says only return me anything that's not 0 when I'm past this point x2. And then how much do I want to contribute from that node to the output? Well, that's determined by W2, which is a learnable parameter. Okay? Exactly. Cool. All right. So just to read through that, relu adds linear contribution to the model. It's not added over the whole domain, hence the model is piecewise linear. With an increasing number of hidden units, the model becomes increasingly continuous. So you can imagine, like, if you just have a model just like this, a single layer with many different hidden nodes to a single output, as long as that is deep enough, however deep that is, that's how many piecewise components you can have in the function, right? So if you have an infinite number, you can represent any function, right? Thankfully, you don't need to have an infinite number because we can have more layers, and then those layers create like many more complex relationships that you can build with less units and less parameters. Okay. Cool. So, how do these learn? We have this function. It's differentiable. We can have these two different losses. Here's the mean squared error that we've seen. There's also another loss, binary cross entropy, which is for classification. We won't worry about that now. We're not going to go into it. But so to learn, we need to find how each weight affects the error. And so we can do that using the chain rule. So that is just multiplying together derivatives such that the previous denominator and the next numerator essentially cancel out. So we just need to be able to find these the derivatives of these different components, right? So we need to be able to find the derivative of A with respect to, which is also our output h of x, with respect to the weights, and then we know how the loss, which is a function of the output, changes with respect to those weights, and we want to know how the loss with respect to how it changes with respect to these W2. So the way we can do that is find, well, how does the output change with respect to A2, and how does A2 change with respect to W2? So that's what we're doing here, right? So how does A2 change with Z2 firstly, actually, so like after, before it's been activated in here, and then how do those scores, which are like the pre-activation values in these nodes, how do they change with respect to the weights in those parameters, right? And then you can just like compose all of that into one product, so that you can find the loss with respect to the weights in the second layer. Okay. And that's just the SGD update rule again. Sorry, I used W here rather than theta, but I guess it's even better to represent the parameters. And the important part is like parts of the equation reappear. So what I've drawn in these like orange channels here, they're in the next equation. So you can reuse them, right? Because as we get deeper models, like these are going to get increasingly complex. And so the runtime of the backpropagation will be controlled by how long is that, unless you reuse it, right? So, well, I mean, it's going to be controlled by the length of the product of values which you need in the furthest layer. But you don't want to be repeating any of them, right? So you can say, okay, let's basically just compute the deepest one and then use all the parts from that to compute the lower ones, and vice versa. Basically, just don't repeat them. And so doing that is called backpropagation. I don't know why that's cut off. And that's the method for training neural networks, just by using the chain rule and reusing all those products. Cool. Yeah, so this is kind of just what, like I mentioned earlier, we build on features output by the previous layer to build more abstract features. Just a side note, you might hear it, like a latent feature is a feature which you don't observe directly. So, well, which isn't in the data. Like if you saw this data as a matrix, you wouldn't be like, okay, cool, I know there's a car in there. That's a latent feature in the data set. It's something you have to abstract. It's something you have to extract from that. So here's an example. This is actually a convolutional neural network, which we'll go over another time, of building hierarchical representations and then building features on each of those previously extracted features to get an output. So it's like in the first layer, we might look over this image, we might find the edges, and then from those edges, we might be able to conform. Okay, like there's these different shapes, there's these different outlines, and then from those things, we can form high-level features. Okay, cool. So a model's going to perform better if it can identify meaningful features, which means that, like, as we learn the weights, as we learn weights of a model, they should basically mean they should learn to represent something something useful, right? It's like, because that will be better at solving, better minimizing the objective function. So it's called automatic feature extraction. I don't know why it didn't show up again. So here you can kind of like visualize, like, okay, if we have just like, say we have binary weights to keep it simple, this might be like the randomly initialized vector of weights, but then really it might be, this might represent a useful feature such that the features that that are in position like 1, 3, and 5, when they occur together, that means like, yeah, like this is a person in an image or something, or like, yeah, this house is suitable for a student, that kind of thing. We're just going to do this like iterative weight update like we did with the SGD on these parameters, of which there's many more of in a neural network, so that they go from something random to something meaningful. And here's like a more intuitive example. Again, this is with a convolutional neural network. That's kind of what you'd see, but it's intuitive to think of this as like images. So, randomly initialized weights. If we move it to here, then when we see this pattern in a particular location of the image, we can see, we'll trigger some activation, which is like, yeah, there's a car in this image. Okay. Cool. The very final thing, talk about in these slides, is computational graphs, and this is like the whole reason for using computational frameworks in PyTorch. Basically, the linear regression which we implemented, it's not logistic, can be written as a graph like this, right? So there's different elements in this graph, and there's different operations which tell you like how to combine them. So here, like, okay, we'll multiply x with the weights to get the scores, then we'll activate those scores to get the activation, and then we'll take the mean squared error between the predictions and the labels to get the loss. Okay. So basically, just like points all about the place, like what variables contribute to what, and how do they do so. So all of these arcs are basically like functions. And what we want to calculate is how does this change with respect to this, i.e. how do we update that weight? And so the way we want to do that is, just like chain rule, cancel all them out, and then find that out. So basically we want to compute each of these things independently and multiply them, right? So the derivative of each operation is simply a function of its inputs. So how this changes is just some function of this and this. So here's a better example. So the rate of change of the activation here is just a function of its inputs here. These x's should be z's. But yeah, rate of change of A with respect to Z is just this. And so if we know what function this is, then we know what operation, what computation we need to do to calculate the derivative of that. So we can just program functions that output the derivative of a particular operation in the graph. And then we can apply them to any variable that appears in our graph as long as we store how they're computed and from what variables. So basically what PyTorch does, what computational libraries do, is like they have built-in functions. So like in this case, like that's a sigmoid function, sigmoid activation function. PyTorch has a sigmoid function, and when some variable is computed from that sigmoid function, it'll be a type of torch tensor, and PyTorch knows that torch tensor was created using the sigmoid function, and it stores that in some data it has about the actual, alongside the actual numbers that represent that value. And so it knows that it was created by sigmoid function, so it knows when you want me to differentiate this with respect to, whatever it came from, then I just have to basically get this function from the software library and then call it. Okay, so we don't have to implement it. We can just let PyTorch do that for us. So that's what we're going to use PyTorch for now. And there's all kind of operations. There's like a linear layer, that's what we'll build there. Activation function, mean squared error. PyTorch takes care of implementing the derivatives and all of the forward passes for all of those functions. Okay. So we'll get onto that in a sec. Let me just take a break and feel free to ask questions, etc. I hope we'll get onto. I'm going to get overrun. But like people will just leave before the morning. But we'll just do like a neural network implementation. We'll just like take that data we made earlier, make it more complex, and then change the logic to PyTorch neural network, change it to the change criteria. It should be pretty simple. Start small and then try and make it bigger, right? The smaller it is, the less computation you have to do, and the faster. So hence, the faster you can do the forward pass, and hence the less memory constraints. But from there, it's like, well, there might be an equal number of computations to do with different models and different depth and layers. It's a really active area of research, and I don't have this one straight on answer. But one thing that we'll be doing later this month is talking about architecture search, which is a point of, the layers, the depth, etc. That's the architecture of the neural network. And so there are kind of like at least some systematic ways to try and search over that space. So like, the problem is that like once you change one thing, once you change the width of one layer, it's like you have to retrain the model to know how well it is, to know how well it's doing. Right? You can't like just evaluate an instantaneous loss because you don't know what that was contributing to a model which had it, or you don't know what it was not contributing to a model which it doesn't have.
While changing the number of neural network layers, how can I make sure that I'm not trapped by overfitting or underfitting?
We
especially for the
Yeah, so just plot your. You shouldn't have there actually. You should plot your losses. Plot your loss. Plot your training and your validation loss. Okay. So, and then test and see like, like so. I mean, yeah, you can do like quantitative testing. So like look at the loss. Does it get to some low number, whatever that low number might be? That's
this is in
subjective.
the validation case, or
In both, so you want both a low training and validation error, right? But the difference in those two can kind of indicate what the problem is.
Yeah.
Like if you have a low training error but a high validation error, then it's probably that your model's underfit.
Yeah.
Sorry, overfit, right?
Yeah.
If you have a high training and validation error, it's probably underfit.
yeah,
Correct?
yeah. But I noticed that some people they use like testing data set, validation data set, and the training data set, validation and testing, three data set there. Some of them they ignore the validation data set, they just divide it to like data set one for test.
Where have you seen that?
Many papers that when they use it, like, especially for when they use the environmental tool, use some analysis for signal processing or performance diagnostic. They used to divide it to three data set for training, for validation, and for testing. So which one is better?
Yeah, you should always use validation testing because the point of validation is that one point of validation is that you can tune your hyperparameters, right? So like what's just different hyperparameters like learning rate, like batch size, like box, like that kind of thing, and then you can adjust them with the same model to see. You basically find the best hyperparameters for the validation set.
Okay.
But you shouldn't do that on a testing set, right?
Yeah.
If you're changing the hyperparameters based on the testing set, again,
Yeah.
you're just looking at the answers,
Yeah.
right? So you shouldn't be doing that, which is one of the points of training.
Is it also is there any idea of split like 50, 50?
It's empirical, really. Just see what works. But like rule of thumb, like I do like 70, 20, 10, something like that.
Okay, 10 is that.
Sorry, yeah. But it's like again with like it's like the empirical distribution. You have to make sure it's representative of what you really want to model. So you don't want to have any of them too small, but you want to keep models as big as possible.
Well, if
right?
you attach them end to end, it's kind of
data
so it's
resources.
continuous, right?
Oh, my brain hurts now.
Yeah, it's continuous. I think that's what I meant. Whereas, because if you have like hundreds, 2 chunks, it's going to be small. I think that's what I meant.
Okay. Let's build a neural network. All right, we're gonna stick with the data we've got, right? Actually, I'm gonna make a more interesting function. I think I have one here. Oh. Okay, cool. That's an interesting function that we can model. But we're not going to be able to do it with the linear function, and I don't know what kind of terms it might need, which aren't linear. So I'm going to use a neural network. So I want to insert above, or
Sorry.
just want to insert a cell below here. Yeah. Okay, cool. All right. So, okay, what do we need to do? We need to we need to build a data set. We need to build a model. We need to define a criterion, and we need to define an optimizer. Okay, so let's build a model. So we'll say class neural network. We'll define the constructor, which takes in number of features, number of outputs, and then what we'll do, okay, sorry, we're going to import PyTorch first. Yeah. Oh no, torch, no. So it will tell you this thing. Oh no, it worked. Okay, cool. Yeah, it might that thing that came up first. It will tell you like put this code snippet in and then run it, and then that'll import PyTorch for you. So now we've got Torch in here. What we're gonna do is we're gonna create a neural network, and now we can start using the PyTorch library. So we'll say self.layers. I find this is the best way to make models, is to say torch.nn.sequential. So from Torch's neural network library, get this sequential function, and what this takes in is just a list of the layers which you want your model to apply sequentially. So we'll say like, and here now this is where it's interesting, because you can just define whatever architecture you want. You can just say, so we'll say first layer, we're going to do torch.nn.linear with a capital L. That creates a linear layer. It takes two parameters. One of them is what we want it, the dimensionality we want it to go from. So number of features, in this case, it's our first layer. And we want it to go to, give me a number, how many nodes we want in our first layer? 10, cool, all right. And then we'll go, okay. Why is that indented? I've done something wrong. Torch.nn.linear, have another linear layer to go from 10 to 10, cool, all right. And then we can go, why is it indenting like that? We'll do torch.nn.linear. We'll go from 10 to the number of outputs. Okay, so that defines the layers for that model. Okay, and then we just have to define a forward function. Okay, now, okay, yeah, we'll do it and then I'll explain that. Okay, so the forward pass is going to take in some input, x, and it's going to return the transformed version of that. So, right, we'll just say return. In this case, it's just self.layers of x, okay? So this self.layers, this torch.nn.sequential, it returns a callable, like a callable sequential object, which when you call it with some input, in this case like x, it will apply those layers and then return the final output from there. Okay, so yeah, cool. Like we built a neural network. Like that was pretty easy, right? But there's a few more things we need to do. Firstly, we need to remember that it's got self in all of these, as I always forget. And then we need to okay, so basically, like, we're not going to have to write all the update parameters, initialize parameters, that kind of thing. Firstly, the initialize parameters, like when we create these layers, essentially, so calling this linear function, what that does is it doesn't do a forward pass of linear layer. It just creates the linear layer, which means in this model, it instantiates a weight matrix, which, say, in this case, has a 10 by 10 weight matrix. In the first case, it has a 1 by 10. Sorry, a 10 by 1 matrix. It instantiates them for us, and it puts those model parameters. Well, what we're going to make it do is get those weight matrices and store them as parameters of this model. It needs the functionality to do that, right? So we need to make this class inherit from torch.nn.module. And this lets us do a few things. So, like, if any layer is defined in this model, it will create the parameters for that layer, and then this model, because it's inherited from this torch.nn.module, will get those parameters and attribute them to this neural network. So we can say, after we instantiate it, neural network.parameters, and then it will return all of the, I think it returns a list or a generator of all of these, of all the parameters in all these different layers, okay? So if we were going to create it, so we can instantiate the neural network like that. Okay. So it's going to take in 1 and go to 1. Can't assign module. Okay, yeah. One thing that we need to do is we need to initialize this parent, this module, right? Like, we need to set it up to do those things which I said. So we need to call a function called super, which means like, I can do stuff with the parent class. So I'm going to get the parent class and I'm going to call init on that. That should solve that problem, I think. Yeah, cool. So there you go, we created a neural network. And then we can do print nn.parameters. So there you go, it's a generator object. So we can do, just to show you, for param in nn.parameters, we can print that. Param. Let's do that. So there you go. There's all the parameters of our neural network, and it's just like torch.nn.module has just been nice and put them in this nn.parameters for us, right? So this nn.parameters is like implemented in this class somewhere in PyTorch, this stuff. So we can just so here's the first one. It's a 1 by 10 matrix. What is that? Well, that's the first layer. Second one, yeah, it's a I don't know, it's a, oh no, sorry, yeah, then this is the bias for that layer, and then this is the 10 to 10 layer, and then this is the bias for that layer, and that's the weights for the next layer, and bias for that layer. That's all the parameters of our model, right? And it's going to sort out everything we need for that. Like, we're not going to have to bother about implementing anything difficult like we did in the last example. Okay, yeah, and you could like extract the individual layers if you wanted, I think by name somehow, but anyway. Okay, next thing to note is let's make a prediction. So let's say prediction is, well, let's just print nn.forward of x. So we've already got x, right? Okay, now what's the problem? NumPy.ndArray has no attribute dimension. Well, that's because to pass data through a model, it needs to be a torch tensor. So we can convert things like our NumPy array, for example, into a torch tensor by doing torch.tensor, like that. Okay, and then run that. okay, this is always an annoying. So yeah, there, like we convert it into a torch tensor and we pass it through the model. The annoying thing, which always happens for some reason, is that there's different like data types. So there's a double and float. A double is like so a float is like an 8-bit number, and then a double is like a 16-bit number, I think. But the parameters of the model, the weights, and the data have different data types, so you need to convert them so that they're the same. So we can do like dot float, or maybe it's the other way around. So we can, yeah, cool. So it looks like all of the model parameters are initialized as floats, but we can convert them to doubles like that. Then we got a size mismatch because we're just taking in one. So actually, what we want to do is say data is equal to torch.tensor of x. Okay, cool. So we'll run that. Come on. Okay, cool. So size mismatch, right? So here what's happening. This is matrix 2, M2. It's trying to pass. So it's trying to do a multiplication of matrix 1 by 10 by a 1 by 50 object, right? Well, we don't want to pass all 50 as one example. So what's happening? Like, really, so if we print the data like that, you see it looks like this, right? Now the way PyTorch reads this is that the first dimension is what is it, Haroon? It's like, how can I explain the way that it reads the shapes of PyTorch torch tensors? It's like the first index is the batch, is it? Okay. So basically, yeah. So look, this torch tensor has a shape of 50, right? I guess it's kind of like really easier for me to show. Okay, yeah. So basically, that's just like that's the only index it has, right? It's only like a one-dimensional thing. When PyTorch reads the reads that data, it's going to read, if there's only one dimension, it's going to read that, okay, that's the example it wants me to pass in. Really, for us, every single one of these numbers is an example. So we need to split them such that it reads, each element of an overall list as an example. So what we're going to do is we're going to do dot. So we'll do data equals data dot. We're going to call a function which works on a PyTorch tensor called unsqueeze. And we're going to unsqueeze the 0th dimension. So what that means is like any dimension that is, by default the 0th dimension, I think. If that just has like size 1 or size 0, turn into size 1. So when we unsqueeze it, look at the moment, it's torch size 50, right? If we run this, now what's going to happen? Okay, it doesn't have a default dimension, my bad. Then there you go. Okay, look, here's the new size, right? 1 by 50. Now this means that, just still giving the same problem. Okay, yeah, I think we need to, we need to unsqueeze the first dimension, actually. All right, looks like we got something going on now. So basically, what we did was we had a list of all the different inputs, but we needed to have like a list of the inputs separated into their own little lists, right? So if we print that, so this is what the data looks like now. Yeah, that's it actually. So here it's like the data looks like, well, I've got this long list of data, and in that data there's all the examples. So now every element in that data list is an example. Okay, so now the shape is 50 by 1, and now it can pass those things through the model. So here's our predictions. I think that's what that is. Yeah. So we printed nn.forward of data. Okay. So we did the forward pass, which took this data and turned into this data by, like I said, doing the forward pass, which returned self.layers, which took our input x, did a linear transformation, did another linear transformation, and then did another linear transformation. Okay. First by a 1 by 10, then by a 10 by 10, then by a 10 by 1 matrix, something like that, just to make the dimensions match. So now we've got a prediction. Okay. So, what's the next thing we need to do? So we made a prediction, and now we just need to do that in a training loop, basically. Okay, yeah, that was what I wanted to say. So note that here I called nn.forward data. But what happens if I remove that and just call neural network of data? Well, it still works. That's because torch.nn.module also implements a call function for this class, such that if you call an instance of this class, like we do there, it runs the forward function. Okay? So you don't need to write .forward. You can just take your model and call it with some data. By default, that does the forward pass, which means you need to define a function called forward in every model you use. If you don't, it will give you a not implemented error, I think. So now, cool. That's working. So we know what's happening there. Now we'll just write a training loop. So we'll do for epoch in range epochs. Do epochs equals 10. Then we're just going to do those things, right? We're going to get, you know what? We'll keep that. We'll keep that up there. Okay, so yeah, we've got our data, we've unsqueezed it, so it's in the right format, it's a torch tensor, and now we can just pass that through our model. So we'll just say, for epoch in range epochs, we want to make a prediction, which is going to be the neural network of the data. And then we're going to, okay, sorry, we're going to do some other stuff first. We've got the data, we've sorted that out there. We've got the model, we've sorted that out there. Now we need the criterion and the optimizer. So we can say criterion is equal to torch.nn.mse loss. So in the neural network library, there's a bunch of different loss functions you can use, just out of the box like that, right? We don't have to implement it, and it doesn't take any arguments either, I don't think. So yeah, cool. That sets up the loss function, and now this. So what this initializes the mean squared error loss, right, and returns a callable function, a callable object. So this object we can now call. We can call criterion with predictions and labels, and it will return us the loss. Okay. And when we return that loss, it will be a torch tensor, and torch will know how that thing was created, which means that we can when we differentiate that thing, it will be able to be automatically done by torch, because torch has built-in functions to compute the gradient of the loss with respect to whatever, right? It has, yeah, with respect to this, or it has functionality to compute the derivative of the loss when it was created by this function. Okay, just like I said, it's like the rate of change of any thing in our graph is just a function of its inputs. So this criterion, when we call it, is going to be a function of its predictions and labels. So then we'll say optimizer is equal to torch.optim .adam, or we could say .sgd, or we could say .rmsprop, whatever. Like they're all optimizers which you can use. If you want to look more into that, then check out the what is it? I don't know. There's details of that on the GitHub under Academy of AI if you want to check that out. Okay, yeah, cool. So we can do torch.optim.sgd. Let's do. This takes in what parameters do we want you to optimize. So those parameters are nn.prediction parameters. And it also takes in a learning rate, which will say, and we'll define hyperparameters up here or something. Okay, cool. Yeah, so then we can pass the learning rate into that. And now, so now we've got everything set up, right? And that was how easy it was to make the loss function and to make the optimizer. So we're gonna go through our epochs. We're gonna go. Like the session meant to end in 1 minute. If you have to go, it's fine. This will be online later. Otherwise, I'm gonna stay around until we finish it, and you're welcome to as well. So we'll make a prediction. And then we will, what we're going to do, we're going to calculate the loss for that. So we'll say loss is equal to criterion of predictions against the labels, which are y. And then we'll say, so now we've got the loss. We want to differentiate that loss with respect to all the parameters, right? And you're going to be amazed, if you haven't seen it before, how easy PyTorch makes this. So what we're going to do is we're just going to do loss dot backward, and that's it. That's it, really. So now this, what's happening is like this loss is a torch tensor returned by this criterion, right? And so in this loss, when we do backward, what torch will do is it will look at everything that contributed to loss, that is like in our case the predictions and the labels, and then it will store in those tensors a gradient, or I think in the loss a gradient with respect to those things, because it knows they came from them, and then in these things it will store a gradient of how they were of what they are with respect to anything that created them. So in our case, in the case of label, nothing created them. But in the case of predictions, well, that's going to find how this changes with respect to where they came from, which is our neural network. So that when we do this loss dot backward, it's going to store in this prediction tensor the rate of change of this prediction with respect to every parameter in our neural network. Simple as that, really. I think it probably puts them in the parameters of the neural network. Actually, it stores some gradients there, yeah, and then and because these things are being watched by our optimizer is going to go to them, and it's just going to and then when we call it, it's going to take an optimization step to update those parameters given those gradients. Right? Is that clear? Okay, cool. There's a really good PyTorch tutorial on that as well, like if you just go to the docs. Yeah, deep learning with PyTorch, automatic differentiation, check that out. That's like everything there. Cool. So yeah, I'll walk you through that in much more detail than I have there. But yeah, like this is working now, right? So we'll do loss dot backwards, and it will store those gradients in those tensors which contributed to the loss. So we'll be able to access them for our optimizer, right? Or our optimizer will be able to access them. However, one other nuance is that when we compute those derivatives, they don't overwrite what's already in the tensors. They add to them. So every time we go through this loop, it's going to add to add to what's already in the gradient. So we need to have another thing, which is optimizer dot 0 underscore grad. So this 0 is the gradients in everything that the optimizer is watching. Okay. Then we calculate the we differentiate the loss with respect to everything that it needs to be differentiated with, and then we do optimizer dot step. Okay, and that will update every single one of the parameters in the model. based on how this update rule is working. So SGD in this case, and it will just change them slightly in the model, such that when we come back to the next loop of this, to the next prediction, this loop here, the parameters of those models will have changed. The prediction will be different. Okay, so what's happening now? So we'll print the epoch we're on. And then we'll print the loss, and that is loss.item. So loss will be a tensor. Actually, you know what? Let's just print the loss first so you can see that. Okay, let's try and run that. Invalid syntax. No, thank you. Torch.optim has no attribute. SGD. Yeah. Nice. SGD. Cool. Yeah, NumPy object has no attribute, requires grad. It's talking about, so here we're talking about y. So because the y is a torch. Sorry, is not a torch tensor still. So we'll say so we'll get the data and then we'll get the labels is equal to torch.tensor y. And then I think we'll have to unsqueeze that as well. No, I don't. All right, let's try that. Right. Loss infinite. Not good. Okay, but one thing to know, like, here's the whole loss first. Like, I just said print the loss, and it printed that whole thing. So we don't really want to print that whole thing. You know, I don't care, like, it's a tensor, I don't care data type, I don't care grad function. I just want the data in that. If it's just got a scalar in this case it has, you know, this item here, the actual numerical data in this object is not a tensor. We can do dot item. Then run that, and then it'll print us just the number. Okay. So now we've got a problem. What's the solution? Anyone? It's diverging. So we try a smaller learning rate, much smaller learning rate, and there we go. Looks like it's going down, right? But it's going down too slow. So what's the solution? Sorry. Increase the learning rate. Yeah, let's try that. All right. Yeah, it looks like it's going down now. See how small we can get it before it starts diverging. That looks alright. Okay, cool. And then we'll do it. Let's do it for 100, and then let's do plt dot plot. I think. So we can so basically, like, the prediction comes out. It's a tensor. We want it as a NumPy array, so we can plot it. So we'll do pred dot NumPy. Right? I think that'll work. And then we'll plot the prediction we'll plot the x against the prediction, and we'll plt.plot the x against the label. Alright, let's see what happens. Can't call NumPy on variable that requires grad. Use var.dchatch.numpy instead. So let's do that. So prediction is still in the graph. I'm not really quite sure of what this is all about, but we need to do detach.numpy. So we need to take it basically out of the graph so that it's not. I don't really know why, to be honest. In order to enable automatic differentiation, PyTorch keeps track of all operations involving tensors of which the gradient may need to be computed, if grad is true. The operations are recorded as a directed graph. Detach methods construct a new view on the tensor which is declared not to need gradients. It's excluded from further tracking of operations, and therefore the subgraph involving this view is not recorded.
Basically, so it goes to not tracking.
Yeah, okay. So, let's try that. Alright, snarly again there.
Linear. You haven't activated it yet, right? So it's a good demonstration of
That is an extremely good point and demonstration. So, I forgot to put activation functions in the model. So like, yeah, like it just collapsed back into a linear fit, right? So even though we put all those layers in, it didn't do anything. So we need to have activation functions in here. So we'll add just, after our first linear layer, we'll do torch.nn.relu, and then we'll do torch.nn.relu again. Alright. Then we'll have a look. Still looks pretty linear. I think it's I think we just need to train for longer. It might also be because it's a really small model. There you go. All right. It's good enough. That's good enough. It's only 4:10. That's not too bad. Cool. So I guess we'll leave it there. It feels like they learned something today. No one? No. All right. Cool. Thank you for coming. Keep updated on what we're doing. Are there any questions? Are there any questions about what we just did? I'll make all of this available. I'll save it and I'll put it on the. And I'll just I don't know. I'll email it to you, or I'll put it on a GitHub or something like that. Yeah. Okay. Cool. So I'll wrap that up and then talk about what's coming next. Yeah. Nothing else to say. Cool. Please. Actually, all right. Just bear with me a second. I'm going to send you a feedback form, and you're all going to fill it in. Okay. Actually, okay. All right. Please, we'll fill that in. If you could just go to this chat and please fill in.
It's not sending.
Strange. It's sending messages too fast. No. I just need to reload. Cool. All right. So please, if you could all just spend a minute now, honestly, we really appreciate it, and it's so hard to get people to fill in feedback. But if you could just do that, it would be really helpful. Especially seeing as we just did that live today, and it's a different implementation. Yep, sure. It's if you just type the hackerhustle.com, and then it will take you to that page, and you can just you can put your email then to fill in if you want to hear about more stuff as well. But then just go to Hacker Hustle TV, and then it's the latest thing I just sent in the chat. I will email it to you as well, just because I should. That'd probably be easier. Either or. Cool. All right. So, other than that, we would just like to announce. So basically, we're going to be doing something over the next month, starting on Monday, which is going to be absolutely savage. I don't know how we're going to do it, but we're going to be live streaming implementations of machine learning from scratch to really state of the art stuff. For a whole month, every day. We're going to be doing, we'll do it at a fixed time, and there will be, and it's basically going to cover all of this stuff so far. We're going to walk through basically everything you need to know if you want to get more involved with machine learning. And we're going to be doing it as we did today, like live implementations. I don't know how this works, so I'm going to Google it. And if you guys want to learn this stuff, then you should come along and join these sessions and learn like we learn, and just try and build stuff. And we really want to build a community of people who want to hack together cool stuff like we do, and use it to just build something cool, or to build something to make some money out of it. And we want to help anybody who else wants to do that to do it as well. So if you're interested, then please just go to the hackerhustle.com, sign up, and then we'll send out an email, I think later today once we've built some more of the website, or tomorrow, about how this month of ML is going to work, what you can do to get involved, and whatever else is coming next, and however else we can help you. Also, just another thing to note, there is a section here on the site called Office Hours. If you have any kind of deep learning problem, or just want help, or want to talk about code, want to talk about something we've implemented, want to just ask some high level stuff about AI, or just want to chat, whatever, you can sign up for Office Hours here. So you can just click Office Hours, just tell us about the problem that you're facing, or just tell us I want to chat, tell us what time you're free on a Sunday, and then we'll send you an email, and we'll do a one-on-one support session with you if you need it. So that's everything I have to say, really, and just the main thing is thank you for coming. But yeah, feel free to leave now. Cool. Thank you, live streamers.